that were very much useful to explore the work in field of electric vehicles and DC microgrid. So these are the domain in which research is progressing, especially those who are related to power electronics and power systems. So this FDP will be like our attempt is that somewhat it will help because every faculty takes about 2 hours. So there is it is not possible that he will cover everything, but yeah, just we will get glimpse of something, and that idea and learning will help us to further progress in our research. So that is our aim. Okay, well, so basically I will be talking maybe when we talk about research, then there are always some new thing coming in the domain, and we talk about that. But every new thing or innovation that is based upon fundamentals, elements of that particular field, right? So we will be talking about the fundamentals in my most of my lectures, which is necessary when we are going to use or invent any new topology, any new control design, like that. So most of my talks will be on fundamentals, which is also necessary if you want to do something new, something novel. So today we will be talking about design and modeling of power electronic converters, and how to design the elements, various elements. Then we will be talking about what is the impact of non-idealities, what we study in the textbooks, the ideal case, and what happens if we consider the non-idealities. Then we will be going for modeling, why modeling is necessary, and other aspects of the converter. So before that, I start with my talk. So we will begin that what is the role of power electronics in various domains nowadays. We will see that power electronics has attracted all the researchers and academicians. Academicians is teaching power electronics long back, but in the research or in the applications, whether it's industry applications or whether it's uh, domestic applications or all applications, power electronics plays a big role. So I will be like kind of in teaching mode and not presenting mode. I will be taking these sessions and where we will be discussing the things in with slow mode, but yeah, from fundamentals. So we know that we all need power. If there is no power for a moment, then our life, becomes too much disturbed. So electric power, when I'm talking about power, electric power is very much necessary, or I can say it is electric energy or electric power is very much necessary for everything. If like some of you have even attended our one more FDP which was taken our director sir, then he said that if there is power is not present even for 1 hour, right, then there is so much loss. All industry will be on halt. All the laborers, technical persons, they will be idle. What they will do like that. So power is, now like summers are coming. So if there is no power for 2 hours, 3 hours, then we all feel that okay, this is too summer. So when power will be there, right? So power is needed. So when we talk about power, we all know that there is a flow. Like we have generation where conventionally we have our steam power or steam power stations where coal is the main source, the power is generated. Then this power is generated at low voltage, generally 11 kV. Then this is step up at generating stations itself. And then this is transmitted. Then during transmission, it is like stepped up to 132 kV or even more, right? So in hundreds of kVs, this is stepped up, right? Then this is transmission system. Then again, it is stepped down and at the substations, then it is fed to the loads. So we generated AC, then we transmitted it, then we again stepped it down, and then again we are getting AC. So what we get on our circuit, that is AC. We all know it. Now the power with us available on the socket is AC, right? And this AC we can process through rectifiers. Then there can be power at input side, which is in nature DC. But on the load side, there can be load which demands AC power, or there can be uh, loads which needs DC voltage. So at the input side, we have AC voltage or DC voltage. Source may be AC voltage, DC voltage. On the load side, there may be load which demands AC voltage or DC voltage. So out of these availability, we need to measure the combination. If there is AC power, and AC power is required on the load side also, it means AC to AC is there. So why we need something in between? But you know that AC has voltage and frequency. Here we have voltage and frequency both sides. So the input side voltage may be fixed, but the output side voltage may be needing the less AC voltage, or maybe needing some different frequency AC voltage. So there is a conversion required, even if we are converting from AC to AC. Similarly, load side there may be DC, right? So the nature of voltage is DC. So we need something which takes our AC input into consideration and provides the DC voltage to the load. Similarly, if we have DC on the input side, then we may need AC on the load side, or we may need DC on the load side. So what we see that out of these 2 plus 2, 4 combinations, like there will be 4 combinations, we should be in a position that our load demand should meet with the availability of whatever power form is, right? So to do this function, we need some device in between, and that device is called switching converter, or we can say power electronic converter. Power electronic converter. Now, as we have already done, these power electronic converters can be classified in 4 ways. DC to DC conversion. So these are called DC to DC converters or choppers. Choppers or DC to DC converters, simply converters, right? So we have fixed DC on the input side, and we need variable DC. We need variable DC on the load side, which may be with same polarity or opposite polarity. So that function is done by DC to DC converters or DC to DC conversion. So this part today we will be talking in very much detail. Then another is that load side DC is there, but source side there is AC. So we need AC to DC conversion, and this conversion takes place with the help of a device which is called rectifier. Rectifiers. So rectifiers inputs is AC, which is fixed, and on the output side we need DC voltage, which is variable, right? So we need rectification. Now if on the load side there is AC, but on the source side there is DC, right, which we use in our PV system and all. So we need DC to AC conversion, and this type of DC to AC converters are basically called inverters. Inverters, right? So our aim on the inverter side is that we should get the desired voltage of the AC waveform, which is typically sinusoidal voltage only, and with desired frequency. So this is provided by inverters. So we will be taking one more lecture later on in this week, which will be dedicated to inverters only. Then AC to AC converters, so like transformer, we can say AC to AC converter, but there is no change in frequency, right? Only step up, step down. So when we need to change fixed AC with magnitude and fixed frequency to a variable magnitude, variable frequency AC only, then we can use the single stage conversion. One is we can do it AC to DC, then DC to AC. This is two stage conversion. Single stage conversion, AC to AC, we can do it using voltage regulators, and we can do it using cyclo converters, or also in advanced form, if we see, we can use matrix converters. matrix converters, right? So all these four types have various topologies which have different attributes, different characteristics, different efficiency. So many attributes are different. So depending upon applications, we choose the particular topology and we proceed further in our applications. So broadly, we can classify in four types. So these power electron converters are having various applications. As I said, in our topic of FDP is electric vehicles and microgrids. So in microgrids and electric vehicles, you will see they are widely used, and even our charger, mobile charger, laptops, computers, then we have drives, traction, telecommunication system, spacecraft systems, everywhere these power electron converters are being used, right? So we take a small example that our laptop power supply. So in laptop, we have a battery which is typically 19.5 volt and 65 watt. Normally standard charger is having these ratings. Now this battery is having 19.5 volt, right? Now this is the single source of the power, which is DC in nature and having voltage about 20 volt. And this single source of power is feeding to multiple devices which are there in our laptop. Now these devices works on DC voltage which is less than 20 volt or 19.5 volt, like let's say processor, microprocessor. There is a processor in every laptop. So this processor works on very less voltage, 3 volt, 3.5 volt, even 1.5 volt, 2 volt, like that. So but source of power is single. So we need to get this low voltage with the help of some device, and we know it is the buck converter. So the source is same, but we are getting the less voltage, let's say about 3 volt over here. On the other hand, in same laptop, we have hard disk. Now this hard disk need to rotate continuously. So we need a high voltage over there. So same power or same input 19.5 volt is converted to high voltage, right? Using DC to DC boost converter. In the same laptop system, we have display backlighting, which needs AC voltage. So same DC is converted to AC using inverter circuit. So we can see that in even if it is simple, it looks like simple, but from power system point, power management point of view, power electronics point of view, there are all converters being used, and moreover, this DC battery also needs to be charged. And we have AC in our sockets, which is typically 230 volt in India, 50 hertz, and then that AC need to be converted to DC to charge this laptop battery, right? So for that also we need AC to DC conversion. It means rectifier is also there. So in single converter, a single system, we are having rectifiers, we are having inverters, we are having DC to DC converters, like that, right? So all converters are being used here. Now we take another example, DC microgrid. I hope it's properly audible and visible. Anupam, can you please confirm?
Yes, sir. Fine.
Fine, thank you. Values. So if it is not there, please let me know if sometime it is disconnected due to any reason. Okay, so let us take one example of DC microgrid, right? So DC microgrid, we know that in microgrid what we have, like I told you, in the conventional power system, we do generate the electricity far away, right? Then we transmit it, then we again step down and distribute it. So generation location is selected based upon certain parameters, right? Like where if I say these steam power stations, so there should be plenty of water available nearby because you need to make the steams. There should be availability of the coal. So by taking all these factors into consideration, we select the site, right? Otherwise, if it was so simple, then we could have one steam power station in every city, every colony, if it was like that, but it is not like that, right? A huge infrastructure is required. So considering all the economic aspects, we need to select the location, and then we need to transmit power, because the power we need at everywhere. Load is located at different places, distinct places. So this is not the case when we use this microgrid concepts. In microgrid concepts, what would you consider that are so huge, yeah, in transmission also huge losses are there, so bulk of losses are there. But in case of DC microgrid, we know that our generation, distributed generation, which we call it to be, that is nearby the load only, that is, uh, like wind power, solar PV, so that is nearby the load. So this transmission losses, these losses are, minimized. That is the beauty. So if we call to be DC microgrid, then we consider that all the uh, sources or loads, they are connected to a single entity, single line, which is having certain DC link voltage, and this is called DC link, right? Now whatever sources we have, whatever load we have, whatever storage we have, all we need to connect to this particular single DC bus. Now let's say we have a small wind turbine. Now wind turbine is producing AC, right? But now my reference bus is DC bus. So whatever AC power is being generated over here, that need to transfer to this DC bus. Now transfer this transfer needs a rectification process. So we may need a rectifier first. So using the rectifier, we convert AC into DC. Then maybe the voltage level is not meeting. If this wind turbines are not generating the enough voltage, then we need to boost it up. So we need a DC to DC conversion. Like that, we connect this wind turbine. Secondly, if we have solar PV also with us, then we do connect the solar PV with the same DC bus. And as we know that the solar PV, the solar cells generates small voltage, like each solar cell has a voltage of 0.6 volts somewhere. Then we connect multiple cells in series, and then we make an module. So let's say if each module is having 20 volt, so we may connect again in series to different modules, and we make an array in series parallel to match the current and voltage requirement. But okay, so let's say this, just consider that this voltage of solar PV panels are lesser. So in order to match, because this is DC in nature, but in order to match this, we need to boost it up, right? So here we need DC to DC boost converter. Now, if this is the battery here, battery, that behaves as source and sink both. So when power is depending upon power is in excess or power in short, this battery helps in both way, right? So battery is connected to this same DC link, and because battery voltage may be something different, DC link voltage is something different. So we connect a again DC to DC converter, but because this power flow is bidirectional, so this DC to DC converter should also be bidirectional. But here in wind turbine, because they do not have any storage, the uh, power flow is unidirectional. So these converters are unidirectional. Here in solar also, but in case of battery, these converters has to be bidirectional. So they are to be designed in such a way. Their switches are to be designed in such a way that they are bidirectional. Similarly, this is the AC load. Now, because load is AC, source is DC, so we need to convert DC into AC. So we need again here a inverter, and this is also unidirectional inverter, you can say. Similarly, DC load, so voltage is DC but load is DC, we could connect directly, but we do not do it. Why? Because there may be the voltage level mismatch. So in that case, we need a interfacing DC to DC converter which matches the DC load requirement, right? So here again we have a DC to DC converter, and now the nature of this converter will be unidirectional. Nature of this converter will be unidirectional. So we see in we see that in the DC microgrid network also, and we can also connect this DC with the grid also. So let's say this is utility grid, right? So with the help of some inverters, bidirectional converters, we can connect this utility grid also. So you can see here in this left side, the solar PV is connected, wind power is connected, storage is connected, even fuel cell also we can connect, fuel cell using the hydrogen, we can generate the DC voltage, and that can be connected, loads can be connected, and this utility grid can also be connected to this DC microgrid. So what we find here that these all kind of converters which we have discussed are being used in DC microgrid. So their depth study, how to design their parameters, how to control their switches, that is the key ingredients of these. Though when you see in a broader sense from power system perspective, then these things does not look anywhere. Okay, this becomes very small part, but these are the main uh, system devices which do real function, right? Which in actually operates and generate the power, right? So their analysis is very important. Now, if we see AC microgrid, so it is similar to DC microgrid only. What does change? Change is that now the reference with us, instead of DC, this reference becomes AC, right? Now, whatever distributed generation, whatever loads, whatever storage is connected, everything needs to connect to this AC voltage. So this PV panels. Now these PV panels, so sorry, this is DC microgrid, what we discussed previously, DC microgrid only. Now this is the AC microgrid. So now PV panels which are producing DC, now they need to convert into AC. So we need DC to AC. It means we need inverter over here. Now we know that when we are having this photovoltaic, then because AC bus voltage may be more, then we have here two stage, right? That we will also discuss in some other lecture. Two stage conversion and then single stage conversion also. The two stage conversion is required when there is large mismatch in the AC voltage and DC voltage magnitudes. So first what we do, this DC solar DC voltage, we use boost converter and we step up. Then that DC voltage, which is the output of the boost converter, is used by the inverter to convert it into AC. So that is two-stage conversion. Now in single stage conversion, what we do, so what I was saying here, like we have the solar PV. So the solar PV is first given to DC boost, right? So this voltage is boosted. Then we have inverter, which convert it into AC. So here we have one DC to DC stage and then DC to AC stage. So this is two stage. In single stage, directly we have solar PV, and in single stage itself, this is DC, we directly convert to AC using the inverter. Okay, so that is single stage. Now wind turbine produces AC and the reference bus is also AC, but to match the voltage we need AC to AC conversion. Now battery, right? So we need DC to AC to DC bidirectional converter which converts DC voltage to AC voltage and vice versa. So for load we need a single direction, unidirection AC to DC converter, and for AC load also we need unidirectional AC to AC converter, or you can say regulators, voltage regulators. So here also, whether it's a DC microgrid or it's a AC microgrid, we do need power converters. Hybrid DC microgrid. So what happens in hybrid DC microgrid? In one area we have one microgrid, which let's say AC microgrid is feasible over here, where this, let's say for example, let's say here the wind is generating good power. This area is feasible to wind generation, so wind power generation. So in that case, we will choose for having AC microgrid because our main source is AC. We can use diesel generators also as a backup if we have. Then we can connect it to the grid also, and then we have AC loads mostly here, so we go for AC microgrid. Similarly, this side we have solar PV in bulk, let's say. So DC, it will generate DC voltage, so having DC grid is good for us. Load is also DC, huh? Storage is also there, battery storage is there. We have, let's say, electric vehicles also. So electric vehicles kind of DC is kind of DC load. So in this case, our DC microgrid is feasible. So both areas are having different set of microgrids based upon availability of the generation and the loads. But these two separate microgrids can also be interfaced, right? There can be some time when this AC voltage, or sorry, this AC microgrid is generating more power, and there is scarcity of power at this DC microgrid side. So this AC may transfer some power to DC microgrid. Vice versa, if sometime DC microgrid is having excess of power, then it can transfer this power to AC microgrid, right? It means we may need a bidirectional. We may need a bidirectional power flow, right? But nature is AC and DC. So we do need a bidirectional AC to DC to AC, right? So whenever we need AC to DC or DC to AC, interlinking converter in between, which will be controlled in such a way that the voltage of both sides, they are in a relation, and the power is transferred from one side to another side. So this is the hybrid microgrid where all kind of converters need to be properly designed and controlled. If we take a electric vehicles example, that what is the role of power electron converters in electric vehicles? So we know that the for a vehicle, the important thing is that this wheel should rotate, right? So who will rotate them? Electric motor, right? Motor will provide the mechanical power to rotate the wheels, right? Now this electric motor, it needs power, right? So it needs power, so it needs AC power. So this inverter is there. Now this inverter needs the DC power. That DC will be converted into AC and will be fed to electric motor, which in turn will turn the wheels, right? So now from where to get this DC power? And this DC power need to be of high voltage. Santanu Mishra sir has described various ratings of EVs in his lecture, right? Now we have with us battery, high voltage DC battery. Now this battery is having certain voltage, and now this is the DC, high voltage DC bus. This is the high voltage DC bus. Now this DC bus needs to be provided the voltage. Now battery has certain voltage, and this DC link voltage has certain voltage. So in order to push the power, we need a converter, right? And this converter feeds the power to this inverter, right? Similarly, we also have, let's say, fuel cell stack also, fuel cell stacks. So this fuel cell stack provides the DC voltage, and this DC voltage now needs to be connected to this, again, DC link of this EV, right? Now, apart from there, this electric motor, there are various other devices, accessories in the electric vehicle which need to supply the power, right? So we have low voltage battery also. So that low voltage battery supplies, the uh, power to these accessories, low voltage accessories, right? Now this battery, low voltage battery, yeah, this supplies the power. Now we have one more component, that is a supercapacitor. Why this supercapacitor is required? What is this supercapacitor? Basically, our battery is there. Battery is having bulk power, but it has a dynamics chemical reactions, so it cannot supply the power instantaneously as much as required. If it was the case, then we could have, there was no speed issue if any amount of power can be drawn from the batteries. But it can give power up to certain range, that is okay. So we can go up to certain speed. But if let's say the vehicle is going on some hilly area, some slope for some time, let's say we are crossing some bridge, we are on normal flat road, then there is a bridge suddenly. So to ride over the bridge, we need some more power, right? Then who will give that instantaneous power? So if supercapacitor is there, then the supercapacitor stores the energy and they discharge instantaneously. So if we need instant power, then supercapacitors are useful. So for that particular moment, for 10 second, 20 second, the supercapacitor may provide that instant power. So that's why supercapacitors are used. So what we learn here, that in this electric vehicle also we need inverters, we need converters, various converters, inverters we do need. And when we talk about the charger, if we need to charge the battery like we were doing in the laptop case, here also we need again rectification, AC to DC rectification. So all kind of converters are again used in our electric vehicle as it was being used in microgrid. So converters plays important role in electric vehicles and microgrids both. Hmm. So if this is again solar powered, no, yeah, again it's a, yeah, it's a the if we are having onboard charger, then this is the case, onboard charger. So as I explained just now, that in onboard charger, in this case we consider that charger is outside and battery is charged and then other function is happening. In onboard charger, we have this charger directly inside the vehicle itself, and we plug it and it charges the battery, and the remaining functions are typically same. All right. So there are various DC to DC converter topologies which can be used for these applications, right? Bidirectional boost DC to DC converter, three level boost DC to DC converter. So because like when we are connecting any load to battery, or we are connecting battery to something, then we normally use the bidirectional converters, right? So the switches which are being used in such topology, they has to be bidirectional. They should have a capability to carry the power, carry the current basically in both the directions. So there should be a diode connected in anti-parallel to the switch, right? So these are few topologies. Then there are few isolated topologies also. This is modular switch capacitor DC to DC converter to increase the level of voltage. So now we come to DC to DC converter. So as you know that DC to DC converters is a device which converts the fixed DC voltage into variable DC voltage by controlling the conduction time of switching devices. So what are various way? If I am given with a fixed DC voltage and I need to have a variable DC voltage. For example, let's say on the input side, I have 100 volt DC. Now my target is to get 50 volt DC on the output side. Okay. Now my load resistance is 5 ohm. So how much current is required? 10 ampere is required. So on the load side, my demand is that 10 ampere current should flow and voltage should be 50 volt. It means I need 500 watt power at the load side. That is my requirement, and source is with me, that is having 100 voltage fixed, and any amount of current can be drawn from here, that is given to me. So what is the way we can do? So the very first way is that voltage divider circuit we can use, right? So it's very simple. We connect a variable resistance in series and we do vary it in such a way that this 100 volt input is here and this is the output 50 volt. Now this output voltage remaining 50 volts, that should be that should be dropped across this resistance, and then I will get 50 volt at the output side. Perfectly, I'm getting 50 volt. My work is done. But what is the issue? Issue is here that you are we are drawing 10 ampere current from here. So 50 volt voltage, it means total power is 500 watt. And this 10 ampere current is flowing through this resistance. This is coming from source also. So source is taking 10 ampere current. This is 10 ampere current. Now this 10 into 100, that becomes 1000 watt. It means from my source, 1000 watt power is being drawn, right? But my load is having only 500 watt. So where the remaining power is going on? So we see that 500 watt power, where it is going on. So this is going on over here because you have dropped 50 volt here, 10 ampere current. It means 500 watt power is being dissipated across this variable rheostat, which is nothing, which is just a in between device, which is neither useful to load side nor to source side. It is just in between. It is the doing work. It is the mediator device which is just executing this work, but it is charging 500 watt, right? It means my efficiency is just 50% if I do in this way. So if I do this for a, let's say, PV plant of 100 kilowatt, then my 50%, 100 kilowatts, so 50 kilowatt power is being wasted. So I cannot tolerate this kind of thing in the high power rating systems. I can do it for a small power rating where 5 watt, 10 watt, 15 volt, this much power rating is there. So here issue is that power efficiency is very low. Also, I cannot get a voltage which is greater than 100 voltage. I can just drop some voltage. It means my output voltage can be less than input voltage. In order to solve this problem, what we did, and again issue is that if I again need instead of 50 volt, I need 60 volt, then I again need to manually change this 50 this 5 ohm resistance to 4 ohm resistance, right? So that is not possible exactly changing to 4 volt, right? It means error may be there in the output voltage if I need some different voltage. So to resolve this issue, we did use linear mode power supplies. We did use linear mode power supplies. So what is the linear mode power supply? We have certain reference voltage here, and this reference voltage is given. Now this is the output voltage. Across the load, we need 50 volt output voltage. Now input voltage is 100 volt. We use a transistor over here, right? Now this 10 ampere current is being drawn from this transistor, 10 ampere current. Now what is happening is here 50 into 10, yeah, means 500 watt power is being wasted over here also, across this transistor also. So what is the beauty about that here? If I change this reference volt from 50 volt to 60 volt, right? And now present volt is 50 volt. I have set this reference to a new volt of 60 volt. So there is a difference of 10 volt. Now this difference is sensed. And here a positive error is generated, right? Now this error is given to this driver. Now this driver will change the base current in such a way that this drop BCE, uh, this drop BCE will change to 40 volt, and we will get finally the 60 volt at the output volt, right? So what is happening here, that in why I'm saying it to be regulated power supply, because if I'm changing the new reference to 60 volt, it will track its own. It will give me 60 volt. If I change it to 70 volt, it will give me 70 volt, like that. But the issue here is that it is drawing 10 ampere, and this 10 ampere will be drawn from here. So this 100 into 10, again 1000 watt is drawn from the input. Output side power is 500 watt only. So where this remaining 500 watt is going? So this remaining 500 watt power is dissipating across this transistor. Now this transistor is having 500 watt power, and this power is in form of heat, right? Now if this heat is not taken care properly, if this heat is not dissipated properly, then what will happen? It will rise the temperature of the transistor, and after some time this transistor will be blown, it will be destroyed, right? So it is necessary that this heat is dissipated at regular intervals continuously. This heat is dissipated continuously. So for that purpose we do need the uh, heat sink. We do need heat sink, right? Now due to this large heat sinks, the size of the um, this linear regulated power supply becomes large, they becomes bulky. So that is the first issue. Second issue is that here again the efficiency is 50% only, because this 500 is being wasted in heat losses. So second issue is heat. Third issue is that heat sink is required, so the size of the supply becomes more. Next issue is that again 100 volt can be regulated to lesser than 100 only. We can get any voltage between 0 to 100, but not more than 100. So that is the again issue. So in essence, if both supplies, but what is the issue resolved here? Issue resolved is that tracking of reference, whatever new value I set, I will get regulated power supply. So poor efficiency, large heat sink required, heavy and bulky due to large heat sink, and because efficiency is poor, so suitable for low power application. And here also the lower voltage can be only, it can be used only lower the output voltage, right? Now why it is called linear power supply? So we know this characteristics of transistor. This is IC, this is VCE, right? So IC is basically this current and VC is this voltage, and this has this kind of characteristics, right? If we increase the IB, then this is having this kind of characteristics, right? So when a switch is operated in such a way that current through this is zero and only voltage is applying. So this particularly this region, this is called cutoff region. This is called cutoff region when switch is completely off, and this region where only current is there, voltage is almost zero. So that region is called saturation region. Saturation region, right? So where switch is on, here switch is off. So apart from these two regions, anywhere if your switch operates in between somewhere here, this is called region, linear region or active region, right? Active region. So because my transistor is now working in this region, linear region or active region, that's why I called it to be linear regulated power supply. And in linear region, when transistor operates, there is huge loss that we all know. Okay, so that is the reason it is called linear mode power supply. But then these things are not solving our purpose when we are going for DC microgrid or electric vehicles. Then what is the way? So let us see what is the way. So this is the supply which is given to us. This is the load which is given to us. Now as a designer, I need to do something in between which keeps me away from all these disadvantages or drawbacks, right? So let us see one arrangement here. Let's say I have this single pole double throw, single pole double throw, SPDT switch, single pole double throw. So it is having one pole, but it can be at position one, and it can be at position two, right? Now let us consider that this is at position one. So when this switch is at position one, then what is the voltage here? If I measure the voltage here and draw it in this graph, then when this is at position 1, then output, this VST is equal to input voltage VG, like this, right? When this is at position 2, then what is the voltage? Because this terminal has come now here. So both are the same terminal, so output voltage becomes 0, right? And I keep on doing so with certain frequency. My position at 1 and 2, 1 and 2 for similar set of times, right? So at 1 from here to here, add 2 from here to here. It means this VG0, VG0, right? Like that. And I say this to be T on, I say this to be T off. The time for which switch is at position 1, time for switch is at position 2. So my T on point T is the total time. T on plus T off, that is the total time. So I define a term D, which is called duty cycle. A term duty, which is a term called duty cycle D, which is ratio of turn on upon T. So now my T off is nothing but T minus T on, right? So T on from here is nothing but D into T. So T minus dt, that is 1 minus D into T. That is a T off. And T on was dt. So sum of T on plus T off is capital T, right? Now if I take the average, but this voltage is not DC perfectly. And if I connect this voltage to load directly, if I connect this voltage to this load directly, then my load will sometimes experience full voltage, sometimes zero, full zero, which was not user's demand. User's demand was that I should get in 50 volt DC, right? So this will not serve. But if I take the average of this waveform, if I take the average of this waveform over one duty cycle, then Vg into dt plus 0 into 1 minus dt upon t, it means d into Vg. It means if I vary the duty cycle this d, then I can get different voltages. That is okay, right? So if we closely analysis this waveform, then this waveform and do its Fourier analysis, then what we find that this waveform is having this average voltage component and also which is D into Vg. So this Vs equal to D into Vg. This voltage it is having, and apart from there are other uh, other harmonics also. So if I can take out those harmonics from this voltage, I can take out those harmonics from this voltage and feed the remaining, then remaining will be D into Vg, and it will be a constant voltage, right? It will be constant voltage. So same thing we do it here. We use a filter. We do use a filter. So let me just okay, so what we do, we use a filter here so that all the harmonics are out and only DC is going this way. So here, this filter is being used, right? Now, in this filter we use L and C, inductors and capacitors only. Inductors and capacitors solves the purpose of filtering. We connect inductor in series and capacitor in parallel. How does they help? Let us see. So this inductor offers a impedance of 2 pi FL, right? And this capacitance offer a impedance of 2 upon omega C, 2 pi FC, right? So what will happen if some high frequency component is there, right? Then this will provide a high impedance and those harmonics will not be entering at this point. And even if some enters, then what will be done? This capacitor again, this is the capacitor, right? So if those harmonics are here, so F is means high order harmonics, if they are entering, then this will provide the low impedance, right? It means if it enters here, then this capacitor will provide them low impedance, they will filter out here, right? And there will be no harmonics over here. So if we tune L and C properly, we'll see the way how to tune them. Then L and C, if we tune them properly, then most of the harmonics, higher order harmonics will be filtered out and we will be getting DC here, right? So that is how this components helps. Now, because this L and C are the additional components, so one may think that if these are the additional components, then they will again increase the cost. They will again increase the size of the equipment, right? But we see that why they are being used, they are being used to provide this impedance, right? So if I use this frequency, what is this F? F is the frequency of operating of this switch. If this is very high, then what will happen? If this is very high, then for same amount of XL, my size of L will be reducing, right? Size of L will be reducing. So this inductance requirement is very less. Similarly, if I'm using F to be very high, then for the same amount of axis, C will be lesser. It means if I have switching frequency to be very high, then the value of L and C will be reduced. And if value of L and C is reduced at higher frequencies, then they further reduce the size of our converter. First thing. Second thing, as I said, here we are either using either keeping the switch on or keeping it to be off. It means my converter is now working in switched mode. That's why it is called SMPS, switched mode power conversion. Either it is on or off. On or off means either it is in saturation region or it is in cutoff region. Either it is in saturation region or cutoff region, not in linear region. It is not continuously on as it was here. It was continuously on. Once your base current was fixed, it was on and this voltage was constant. But here this is not the case. Either it is on or either it is off. So when this is on, we can see when switch is on here, switch is on, then voltage is very less. So this power loss V into I, ideally voltage is 0, then power loss is 0. When switch is off, then current is 0, so power loss is 0. So ideally the loss in this switch is 0, and practically if there is some loss, then that is very less. It means the loss in the switch is very less, so the heat sink requirement will also be very less because there will not be much temperature rise, so losses will be less. Now what about this L and C? L and C are also ideal, right? L and C are also, if ideal, then they do not have any losses in them, lossless. So if I talk about this entire intermediate circuit, the switches L and C, they are consuming zero power ideally. It means whatever power output is there, same amount of power input is required. Or if we consider them to be non-ideal, we will see the impact, L and C and switches. Then what will happen? Only small losses will be there, and small losses will be required from the input side. Only small losses will be required input side. So input side will provide 500 plus some amount of losses, 5-10%, right? So in this case, efficiency is highly improved. Ideally, it is 100%. Practically, it is more than 90%, right? Even 95, 98, 97, 98, right? So that depends upon how better we use L and C and switch like that. Hmm? So here what we see that efficiency increases, hmm? And there is no much rise in temperature, so very low loss, due to which only efficiency is high. Then cooling requirement is less because loss in the switches is very less. And if you use these switches at high frequency, then L and C size also gets decreased. L and C size also gets decreased, due to which the overall size of the converter becomes very less, right? And one more thing which was creating problem over here. So efficiency problem is solved, heat sink problem is solved, heavy bulky problem is solved. We use high frequency, low power application problem is solved. Other problem was that if we need voltage greater than the input voltage, then what to do? So that is also possible when we are using the switched mode power conversion. We can rearrange the L and C and the switches position such that the output voltage is higher than the input voltage. Well, so this is in nutshell DC to DC converter. We have certain input voltage, we have certain output voltage, so we have a DC gain, right? And now we want to vary this gain. Then how to do it? We have a control variable, control signal called to be duty cycle. So if we do meticulously operate the converter switches at a particular duty cycle, we can get the desired output voltage. So that is the things. What is inside this box? Inside this box, there is magnetics, which is used for energy storage. There are capacitors. So we know that capacitors and magnetics used as a filter. So they are there. Then there are devices, semiconductor devices, IGBT, MOSFET, like that, transistors. So if they may operate in linear mode, then it is called linear power supply. If they are operating in switched mode, then it is called switched mode power supply. Right. Then these registers, basically registers are being used for uh, load only, for load only. So these are the different components. So based upon that, there can be various topologies. Based upon the arrangement of these switches, there can be various topologies. So we have switches here, inductors, capacitors, then load, then input supply, right? So one topology, we will be discussing this topology in detail. So first one topology is called DC to DC buck converter, in which output voltage is less than input voltage. Another topology is called DC to DC boost converter. We can see here the position of the elements has been changed, and in this case the output voltage can be obtained greater than the input voltage. Then we have DC to DC buck boost converter. So in single topology itself, we can obtain the output voltage which is less than the input voltage, output voltage which is the less than the input, more than the input voltage. So both we can obtain by using the duty cycle properly. Then we have DC to DC cuck converter. So this is a fourth order converter. What is a fourth order converter? We will discuss when we discuss the modeling. Then its output is like V output equal to D upon 1 minus dBg. Minus sign is coming here. So minus sign shows that the output voltage polarity is reverse to input voltage polarity. Then we have so this is the buck boost converter, and this is its a relationship, gain relationship with duty cycle. It's a linear, it starts from 0 and it goes up to be in as duty cycle is 1, right? Boost converter, so when duty cycle is 0, output is same as input, it means gain is 1, and as duty cycle reaches to 1, the output goes to infinite. As per this formula, if I put d equal to 1, the output gain will be infinite. So my question is there, if there is this boost converter can provide the infinite gain, then what is the necessity of other topologies? We will see that in practice it does not happen that we can get any kind of voltage gain from the boost converter. It is not true, because for a practical converter we will see it today itself. Then buck boost converter topologies, there are various topologies. Like this is a basic second order topology. So how to define the order of converter? The order of converter depends upon the number of energy storage elements being used, right? So like this is a one inductor, one capacitor. So this is the second order topology. We call second order. Similarly, in buck converter, one inductor, one capacitor. In boost also, one inductor, one capacitor. In buck boost also. In cuck converter, we have two inductors, right? L1, L2, C1, C2, right? L1, L2, here also C1, C2, right? C2 is the output capacitor. And in SEPIC converter, so here SEPIC converter, two. Am I audible properly?
Yes, sir. Fine.
Well, okay. So cuck, SEPIC, and zeta. So what is the difference? The magnitude for a particular duty cycle is same in all three cases. So what is the difference? When to use which converter? So if you see here, this is our input side, right? This is our input side. Now input side is directly connected to inductor. It means here the ripples will be very less. Almost continuous current will be drawn from the supply. And here also this inductor is connected at the load end. It means again the this current will be continuous. It means your capacitance value will be very less. Most of the ripples will be filtered out by this inductor only. So input current is continuous, load current is continuous. But what is the issue? Issue is that this output voltage polarity is different than the uh, input voltage. Just a minute, please. Okay, so in SAPIC converter, this problem is resolved. The polarity of the output voltage remains same, but because the position of components has been changed, it means L1 is here, L2 is here. Now here this is diode is there, right? Diode is there, due to which this current becomes discontinuous here. This is not continuous, and due to this discontinuous nature, there is more ripple, and to remove those ripples, this capacitor requirement is more, but input current is continuous. Now third topology zeta, in this input current is discontinuous, but output current is continuous, and load polarity is also okay. So if we make one just comparison, so we can say this is CUC, here it is CPIC, here it is zeta, right? So we can say input current, output side current, and we can say polarity. So in first, this is okay, this is okay, this is not in favor, opposite polarity. In SAPIC converter, this is okay, output current is not continuous, and this is favorable. In zeta converter, this is not favorable, but output current is continuous and polarity is also same as input. It means now depending upon application, whether we need continuous input current, whether we need continuous output current, whether we need polarity to be same, we need to use particular topology, right? Another thing, if this converter, first normal buck boost converter was providing me the same gain, then why if we should go for cup converter? So the reason is here that if I take the amount of power to be transferred, amount of power transferred to be same, then what is happening here? This power need to be transferred through this inductor only, right? And in order to transfer the bulk amount of power, this inductor size will be more, right? But here this capacitor, you can see there is a capacitor in all three topologies that is being used to transfer the power from input to output, right? So when you are transferring power through a capacitor, then the size of capacitor is less in comparison to inductor. So that is the reason this capacitor here, this energy transfer takes place through these capacitors, which reduces the size of the converter for the same power level. That is the reason uh, this fourth, which one should go for fourth order converter, right? So you got the basic difference. Now you know various applications are there where we sometimes use these rectifiers, these converters for unity power factor applications. So if you use cup converter, SEPI converter on the input side, then they will draw continuous current and it will be easier to use them, right? So how this is how we choose a topology based upon the applications. Now for a converter, what is the desired feature for a converter when we are going to design? When we are going to design a good converter, then what are the feature we look for? So first is good line regulations. So what is the good line regulations? It means this is, let's say, this is a converter. You are giving some input to this. You are getting some output here, right? So if this input voltage changes slightly, right, then my output voltage should remain constant. If this is my output voltage, then this should remain constant. That is my good line regulations. Good load regulations. What is the good load regulations? Good load regulations means if there is change in the load, then also load means, when I'm saying load means load current. So when there is change in the load current, then also my uh, output voltage should be regulated. Output voltage should be regulated. That should remain constant. That is the second desired feature. Third desired feature is good transient response to the system disturbance. Now let's say this is my input. Let's say for buck converter, this is 20 volt input, and output is somewhere 10 volt. Now at certain interval, this input has changed to, let's say, 22 volt. Now because input has changed, so my output will try to change. But if I have a good controller design, then my output will again should reach to 10 volt, right? Now during some period, this transient will be there. After that, transient is over, my system is reaching to steady state. Now during this period, I have certain oscillations, undershoot, overshoot, and also the steady state error. Sorry, not steady state error, settling time, settling time. So my purpose is that even if this disturbance is present, this overshoot, undershoot, and settling time, that should be minimum possible. Then I will say my system is responding well to the disturbances. So that is good transient response. And the last one is remain stable in all operating conditions. Our system should remain stable, in all operating conditions. If system is unstabilized, then it is not good. So system should remain stable in all operating conditions. So these are, it means whenever we are designing a controller, then we should also analysis its stability, that under what circumstances it may go to unstable mode, that we should analysis. And if possible, we should retune the controller so that it is stable in those circumstances. If not, then obviously we should say our converter is stable under these particular constants only, that we should state, right? So these are the desired features. So when we are analyzing DC to DC converters, so there we can broadly classify these into three categories. One is first design of the converters, then modeling of DC to DC converter, mathematical modeling, and then controller design of DC to DC converter. These three are the fundamental aspects of any DC to DC converter, irrespective of the applications. So you know that in DC microgrid, these converters falls in primary control. So tertiary control or the secondary control, they all finally direct to the primary control only. They do upper calculations, and finally they will say to this primary control, yes, perform this task. Then they need to perform the task in actual, right? So they should be well controlled, well designed, right? So we will go in our today's lecture and coming lectures in detail to these three topics. So first, let us come to the design of DC to DC converter. So we will take here 5-minute break. We will be back at 3:30 again. Okay. So we'll take 5 minutes break. Meanwhile, if you have any questions, please please type in the chat box. So whatever so far covered, I will try to answer as we resume in 5 minutes. You can type. Thank you. Any doubt, please? Okay, madam. Okay, wearing design, sir. Can you please share the relevant standards followed in the design? Yes. Okay. So many, madam. Okay. Yes, ma'am. We will be design. We will be discussing the what like what are the different things which we need to follow while doing the designs for this in coming today only. Today's session also we'll be discussing in detail. Well, okay. So we proceed further. Welcome back. Okay, before proceeding to the design, then let us see what is the switching characteristics. We have seen that every topology is having a switch, right? Every topology is having a switch in this. Like switch can be IGBT, MOSFET, right? Like we have conventionally SCR or thyristor, BJT, like that, right? So now this switch is, which we normally represent like this, diode is also a switch, which is uncontrolled switch. So if I talk about diode only, let's say diode, first, let's say diode, and I do its plot, characteristics plot, then how can I plot it? Let's say this is the diode, its characteristics. This is its voltage, this is current. Now this is P, this is N, I, this is V, voltage across this. As soon as I'm applying certain voltage, which is just positive, right? Then ideally, this diode should be on and it should carry current. Because ideally it should be on as soon as I'm just positive and it should carry current. And what amount current it should carry? It should carry any amount of current. It should carry any amount of current when I'm just applying a positive voltage. And when I'm applying a negative voltage to this, when I'm applying, let's say, so this is we call it to be forward bias. And when I am applying a negative voltage, this is P and negative voltage, this is reverse bias, right? So in this case, this diode is expected that there should be no current flowing. There should be no current flowing from this N to P, right? Or you can say cathode to anode. And entire voltage, whatever voltage is there across this PN junction diode, that should be blocked, right? So this is ideal case, ideal characteristics of a diode. But we all know when practically, how does it behave? Practically, if I plot it again, then this is I, this is V, this is 0. Now, practically what happens, as soon as I'm applying certain voltage, then up to certain range, this diode will not on, right? When this forward voltage drop is there, 0.7 volt, we say it to be almost 0.7 volt. After that only, this PN junction diode will break, and after that this will carry the current, and this current is also not in this way. This current will be certain in this way. It means there is certain resistance, internal resistance RD. Based upon that, there will be certain voltage drop, and accordingly it will carry the current. So this is the characteristics ideally, if, not ideally, practically, if I say. And when I apply the reverse voltage, then what will happen? There will be some small leakage current in microamperes here. And I keep on increasing voltage, then there will be more current, but certain position will reach when it's not like that I can keep on increasing the negative voltage and it will block every amount of voltage. No, after certain voltage, there is avalanche breakdown, right? And after that breakdown, that particular voltage breakover, we call it to be reverse breakover voltage. After that voltage, this diode, this breakdown will take place and huge amount of current will flow through the diode and this diode will damage, right? It means in practical switch there are limitations, but in ideal switch there is no limitations. So this is what is difference between ideal switch and non-ideal switch. So we start with ideal switch. So ideal switch can carry any amount of current. When it is switched on, then there is no limit on the amount of current, known as forward current or reverse current, that the device can carry when when in the conduction state. So it means when this is on, then it can carry any amount of current. There is no restrictions. But in practical switch, it is not there. If you go through the data sheet of every switch, then it has certain current limits over it, right? Beyond which, if you operate that device, then there is a chance that this device may damage, right? So that defines the maximum current ratings from the data sheet. The manufacturer of the device defines this limit, right? So there is a limit. But ideal switch should be able to carry any amount of current. Then there is no limit on the amount of the device voltage, known as forward voltage or reverse blocking voltage, when the device is in the non-conduction state, right? It means when device is in off state, then any amount of voltage should be blocked by it. But we can see here there is maximum amount of voltage in practical case which it can block. After that, it will not block; it will break down, right? But in ideal case, it is expected that it should block the infinite voltage, right? It should block the infinite voltage. Zero on state voltage drop when in the conduction state. So ideally, if this is on, then there should be no voltage drop. But in practical case, there is voltage drop. There is voltage drop due to this RD and some voltage also. Infinite off resistance. When this is off, then there should not be any current flowing through this, but we can see here a small amount of leakage current is there. It means the resistance is not infinite. It has certain resistance due to which, though that resistance is very high, but still due to which there is some current, leakage current, but ideally it should not be there. No limit on the operating speed of the device when it changes its state. It means if it is the ideal device, then we can operate it any frequency, desired frequency. But we know that in practical case, every switching device has certain frequency, like IGBTs works on low frequency, MOSFET works on high frequency, right? And now these gain devices, SIC devices further work on more frequency, right? So range is limited, it's not infinite, right? But ideally it is possible. So what we see here, this is the ideal switch. So when switch is on, then there is a voltage across it. And no, when switch is off here, then there is a voltage across it and current through switch is 0. When switch is on, then voltage across this is 0, but it is carrying some amount of current, right? Like that. And again, this is repeated. So if I calculate the power across the switch, then this is the voltage, this is the current. So power will be multiply of voltage and current, so that will be 0. Here, if I calculate in this period, then voltage is 0, current is having some amount, but product is 0. It means loss in the device is 0. So in ideal case, the power loss is 0. But if same switch is having or is being implemented or being analyzed practically, then what does happen? So this is the case when switch is practical switch. So practical switch has limited power handling capabilities. That means limited conduction current when the switch is in the on state and limited blocking voltage when the switch is in off state. Right? So it will be having limitations on current and voltage. That's the reason every datasheet mentions its voltage and current limits. Right? Limiting limited switching speed that is caused by the finite turn on and turn off time. This limits the maximum operating frequency of the device. Why does it so happen that there is restrictions on the frequency? The reason is that when switch is, let's say this switch was off here, this switch was off, so there is certain voltage. When off, then current is almost zero, let's say. Now when you suddenly say this switch to be becomes on, now this voltage, this current which was almost zero, now this current will not directly rise to the desired value. It will take certain time, because this is what is switch. Switch means some material, so material will take some time to respond, right? So this material takes some time to respond. Similarly here also, so this is called turn on time. Similarly, when switch is once on, then voltage drop is there and it is taking some current. Now you are saying it to be become off. Now it is not suddenly becoming off, it is again taking certain time to become off. So this is called T off. So there is certain limitation on and off. Now on time is required, off time is required. So now this time is fixed, on time and off time, right? So due to this on time and off time, because now this time you have to consider at least and some more time, right? So that total time is depending upon T on and T off. Now if it is depending upon T on and T off, then you cannot have any amount of frequency. So frequency is also limited. Now because switch is not ideal, so when they are on, then there will be loss. When they are off, then also there will be loss. So finite on state resistance and finite off state resistance. It means there exists forward voltage drop when in on state and reverse current flow when in off state. So that you can see here, even if switch is off, then ideally it was expected that current should be zero, but it is not zero. There is some amount of current which is called leakage current is flowing through the device, right? And when device is on, then it is carrying the current, but we expect that when device is on, then the voltage across the device should be zero, but it does not become zero. It has certain voltage which is this voltage, which is this voltage. Now so this is called forward voltage drop. That means we have forward voltage drop, we have leakage current, we have limitation on switches, right? So because of the above characteristics, the practical switch experiences power loss. Now, if we talk about the power loss, then here V off is there, but current also exists, though very small. But if I take the product of them, then there will be some product will be there. It means there will be power loss. Now here voltage is existing, current is existing. So multiplication of both if you take, then this multiplication means this loss is there. Similarly here voltage exists, here current exists. So the product of both, there is again loss. Again this voltage is increasing, current is decreasing, but product is having some non-zero values, which is here. So what does that mean? That this period is transition period when switch is becoming on. This is also transition period when switch is becoming off. So during both the period, during switching, during transition, there is loss, and this loss is called switching loss. Similarly, when this is in conduction mode, this was the off, this was the on, there is again losses. These losses are called conduction losses. So total losses will be switching loss plus conduction loss in a switch. In a switch, total loss will be given by conduction loss plus switching loss. Now, these losses are significant. Previously, what we've seen here, these losses are 0 if ideal case is there, but if non-ideal case is there, these losses are not 0 and they contribute the drop in efficiency. So the calculation of these losses becomes important if we are designing the power supply for a reliable application. Okay, so how to calculate that? So this is our voltage across the switch. This is current across the current through the switch and product of them. So if I want to find the average power across a switch, which will be given 1 upon Ts over a switching period integration from 0 to T and product of Is and Ts. So basically this is nothing but we can write in that way that P average is nothing but 1 upon T 0 to T instantaneous P into dt. So P is nothing but VSW into ISW. So this gives me average power loss in the switch. Now we have seen that this power loss is of two components. One is average P average switching loss plus P average conduction loss. So how to find them? So this is the calculation of power loss in switching device. How to do this? So in order to calculate this, we need the expression for this current and voltage. We need the expression for current and voltage. So once we are given the characteristics, we can find the voltage characteristics during different time periods. So there are different time zones in which different current and different voltages are there. So what we can do, we can write those currents and voltages, right? So and then put those equations here, multiply, integrate, and then find the expressions. Okay, so that's what it is being done here. So P average switching, how we can calculate? Because the switching losses are during this transition period only, this period and this period. So that's what we have done, 0 to this T on ISW VSW dt plus this period ds minus T of to dt minus T of to dt. During this period we will integrate the product of these two equations, right? So this is switching loss. Conduction loss, what, how we will do conduction loss? So for conduction loss, this is the conduction loss, we will do this part, T on to ds minus T off, then remaining is ds to T. We will write the equations. So that's what T on to dts minus T off means this period. What is the value of voltage? V on, which have we written. What is the value of current? I on, which we have written. The another period, what is the value of current? Value of current is here I off. Value of voltage V off. Correct? So like that we have found this to be average conduction loss. So now in comparison to TS, this T on plus T off is very less. So it can be neglected. If it is neglected, then this is I on V on into D plus I of V of into 1 minus T. It means we have found the average conduction loss. So this part is calculated. Now which part is left? This one. Now this one will depend upon the this equation, right? Now these are the not very specific non functions. So what we can do, we can just approximate them to a line, right? So if you see the original characteristics, so they are a bit non-linear, right? So to approximate this, we can make it linear, right? So if we can make it linear, now we know all these times stamps and current voltages here. So all those points are with me, so I can write the line equations. And once I get the line equations, then I can find the current voltages, then I can simplify. That is being done here, right? Over here. This is approximated as a line, right? Now these line equations I can find, this I can find, this I can find, this I can find. Once this is known to me, I will put, so these this is same thing is here, huh? So this is a linear approximation here. So for like let's say I want to write ISWT. So where is my current? This one is current, right? So from 0 to t on means this period. This is my line equation. From here to here, this is constant I on. From here to here, what is this? This equation. Then again, it is I off, right? Similarly, I can write for this voltage also. So these equations I can get easily after linear approximations. Now for every time period I have current and voltage equations, so I'll put them back in this expression. I will put them back in this expression, and if I put them back in this expression, then yes, then I will find these power expressions in this different time zones, right? So I can integrate them, and on solving I am getting this equation. So this all is given in a book, Isa Butterse, right? Isa Butterse. You can uh, refer that book if you want to power electronic circuits. Okay, so after simplification we get this equation. So this is average power. Now this average power has two components. Okay, this has two components. One is this one, another is this one. So this is corresponds to conduction loss, and this is corresponds to switching loss, right? This is corresponding to switching loss. So what we see here, T on and T off, they are almost negligible. So we neglect them, then TS will cancel out. So this term will be just V on and I on. Now this term is depending highly, means this conduction loss is depending highly on V on and I on, which is the current and voltages when switch is on, right? But if you see this expression, then T on plus T off, they cannot be neglected, right? And here this is 1 upon T. So 1 upon T means P average is proportional to 1 upon T. That means this is due to P average due to switching, So P average due to switching, that is proportional to frequency, right? And this is basically switching loss. This is switching loss. It means switching loss is proportional to frequency. So more the frequency, more will be the losses. That's what we say, that more the switching, then switching losses will be high. This is the reason that more the switching losses will be high. But we know that this T on and T off, they are proportional to switching loss. So if there are switches which operates at high frequency, but the T on and T off is less, right? Then this product of both, if that is lesser, then our switching losses will be reducing only, right? So this has two components. One is total switching loss. Second is giving total conduction loss. So as the frequency increases, the average power loss increases linearly because that is proportional to F. Also, the power dissipation increases with the increase in the forward conduction current and the reverse blocking voltage. So that is there. Yes, forward conduction current I on and V off. If they increases, then losses also increases, right? So that's how this uh, switching losses are very important for converter analysis. Okay, now we will see. So we'll take again any questions by you before moving to the next topic in the continuous flow. Any query from your side is welcome. I'll wait for 2 minutes. If there is any query, please type or ask. If there is any query, please ask. Well, so we go ahead. If there is no query, you may ask in last also. Okay, so now we come to the analysis of DC to DC converters. So we start with the buck converter. Well, so for buck converter in steady state, we have analysis in almost all of the books. Now we'll see that how does it behave in transient mode. Before reaching to steady state, how does it behave? So this is our buck converter, right? And if you specifically see, then basically we do use, no, not this. We do use a switch over here, right? Then like this, we do use a diode here. This is a buck converter, right? So when switch is on means at position 1, diode is off. Then our like this diode is off and this switch is on. Then this is the equivalent circuit when switch is on. When switch is off, then this is the equivalent circuit. Switch is off and now diode is on. So this is the equivalent circuit. Now we will analysis these two circuits. Yes, later on. So that is okay. Switch is on, then this is the circuit. Switch is off, then this is the circuit. When switch is on, then what happens? This diode becomes reverse bias. That is the reason it becomes off. We will see later. Now, as we discussed earlier, this is the waveform which we are getting across these two terminals. But if we are using this filtering circuit, then this will filter out the harmonics and we will get a almost DC voltage across here. So this is what shown here, right? Ideally it should be this one, but after filtration we will get this kind of waveform in which again there is a DC component and again some ripples are still left. It is not perfectly ideal, but it is not kind of this waveform. It is not kind of this waveform. It is near to DC only, but still some ripple is there. So when we are doing analysis, and this obviously these ripples are very less than this average voltage, because we design L and C properly. When we design the L and C properly, then these ripples are very less. Okay, so this Vt is almost equal to V. This Vt is almost equal to V. It means this output voltage is almost DC. That's how we do. Okay, so in well-designed converter, the output voltage ripple is small, hence the waveform can be easily determined by ignoring the ripple. That we will consider. Now, this is the circuit when switch is on. So this is the period from 0 to dt, let's say switch is on. So for doing the analysis of any converter, what we do, we define the direction of inductor current, we define the polarity of inductor voltage, we define the direction of capacitor current, polarity of the capacitor voltage, like that, and this is your output voltage. And we do write two important things: all the voltages across the inductor and all the currents across through the capacitor, that we do write. So in this case, what is the inductor voltage? VL. VL is VG, this input voltage, minus this V. So this is the inductor voltage. As per the small ripple approximation, we can consider this a small Vt to be capital V, neglecting all the ripples. So this is our equation for this. Now VL is nothing but L di by dt, right? So VL is L di by dt, which is equal to Vg minus V. So from here, this di by dt, that is VL upon L, it becomes Vg minus V upon L, right? So this is the rate of change of current, right? Means with this slope, your current gets changed or gets increased in case of switch is on. It means this output voltage, because this is a buck converter, so output voltage is always less than the input voltage. It means this slope is positive. If slope is positive, it means with the time increases, the current also increases. So this slope is positive. Okay. In mode 2, when switch is off, so that mode is valid for dt to t. So switch is off, diode is on now. Why this diode is on? If you see here, this diode was connected here. This diode was connected here, right? Now your switch was on from 0 to dt. At time t equal to dt, you forcefully made the switch to be off. Now this inductor current, which was increasing, where it will go? It needs some path. So this current flows, this inductor current flows through this diode and make it switch on, right? This inductor current try to reduce. When it reduces, then this voltage reverses across the inductor. Voltage polarity reverses, and this voltage polarity turns on this diode, and this current is having a path through, finds a path through this diode, and this switch is already off. So that's how the circuit is. So in this case, VLT is equal to minus VT, and using a small ripple approximation, minus V. Now this is same as L di by dt. From here, VL is equal to L dIL by dt. From here, dIL by dt is minus V upon L. V is positive, L is positive. It means this slope is negative. So slope is negative means in this case the current is decreasing. In previous case the current was increasing. This is the trend inductor current will follow. So the inductor current changes with an essential constant slope. Now let us analyze this for this. So I'm just writing these two equations, Pg minus V upon L. So slope here is di by dt is Vg minus V upon L, and in this case this is minus V upon L. Good. V upon L. Right. Now let us see that before reaching to steady state, how this current waveform behaves. So at very first cycle, very first cycle, our inductor is rest, capacitor is at rest, everything is rest. We have just turned on the switch. Now, as soon as we turn on the switch, this is the first circuit which we come across, right? Now, everything was zero before that. So now this di by dt, because this V is zero, this V is zero. Now, this di by dt at this step, it will be di by dt, that will be Pg upon L, right? With this slope, this current will be increasing because IL0 is 0. This current reached to this value. Now after that switch is made off, and this is the slope di by dt equal to minus V upon L. Because initially there was no voltage across this because capacitor was relaxed. So in very first cycle, when switch is off, this di by dt will be 0. It means at this position, your di by dt is 0. So di by dt 0 means slope is 0. It means whatever value is available here, that value will continue till this point, right? That value will continue till this time. Meanwhile, during this first switching cycle, capacitor slightly gets charged. Now when again switch is on, then we again go to this mode 1. Now in mode 1, we follow this equation. Now because value of V has slightly increased, so in this case, this slope Vg minus V upon L will be slightly decreased, right? Now it will keep on increasing like this, but slope will decrease, current value will increase, slope will decrease. Now when switch is off, then this circuit will follow. Now equation here is minus V upon L. Now V has got some value. So this V upon L is not now 0. It has some value V upon L, but slope is negative. It means this is not constant. This slope negatively increases. At this point again switch is on. When switch is on, then again V increases. Right? V increases. It means this slope further decreases. If this slope further decreases, then V value increases. So this slope increases, this decreases, increases. Like that it is happening. And after few cycles, there will be a steady state when this slope and this slope both becomes equal. Both becomes equal. And then we say that a steady state is reached after a certain number of cycles. So this is how this converter progress. And when there is equilibrium, then we will say that at any two points the current value is same, right? That's how the transient behavior of converter is there. Now another analysis which we all do, that is the steady state analysis. So for any DC to DC converter, while we are doing steady state analysis, then we do follow certain properties. The first property is that in steady state, we consider that inductor current has settled and that is periodic. It means same current, inductor current waveform is repeating, right? So if I take the value at certain point, so after t time, right, same value should be there. After t time, same value should be there. Then I say that steady state has reached. It means ILT plus T should be equal to ILT. That is the first principle. Second is that average inductor voltage is 0. In steady state, in all DC to DC converter, the average inductor voltage is 0. That is VL equal to 1 upon T, 0 to T, VL lambda DL lambda. Average capacitor current. So in a capacitor, the average capacitor current that should be 0 in a capacitor. For a inductor, this average voltage that should be 0. Now, if converter is ideal, then there should not be any loss. Input power is equal to output power. If converter is non-ideal, then input power should supply the output power as well as losses. So these are the few fundamental things which we apply while doing the converter analysis. So as the title was also the impact of non-idealities, so we'll see that how converter behaves when it is ideal, how converter behaves differently when this is non-ideal. Okay, so this is DC to DC converter. Ideal first we will discuss, then non-ideal. What is the different elements in non-ideal, that we will discuss. So first ideal we discuss. So while analyzing the DC to DC buck converter, we follow following assumptions. The converter has reached to steady state. Inductor current is continuous. So what is continuous inductor current? So this we call that converter is operating in continuous current conduction mode, CCM. A converter operates in two modes. One is CCM, another is DCM. Continuous current conduction mode. So this C stands for not conduction, it stands for CC stands for continuous current. Similarly, DC stands for discontinuous current. Discontinuous. So when we say a mode or a converter to operate in CCM, and when we do say a converter to operate in DCM. So every DC to DC converter will have at least one inductor or maybe more. So if its inductor current, right, that is always greater than 0, inductor current is always greater than 0, then we call it to be CCM. And if there are even one inductor or multiple inductors, out of all inductors, if one inductor is even if one inductor is having the value of inductor current 0, having the value of inductor current 0 for certain time, even for certain time, let's say this is 0, this is T, then this is T, then we call it to be discontinuous current conduction mode. It means it is not always greater than 0. It is 0 for certain time. Obviously, it will not be negative, but it should not also be 0 for certain, for even for certain time. Even if out of many inductors, one inductor is having this discontinuity, then entire converter is called to be operating in DCM, discontinuous current conduction mode. But if all the inductors are having the current greater than 0 all the time, then we will call the converter to be operated or being operated in CCM, continuous current conduction mode. So that's how we difference CCM and DCM. Third assumption is that capacitor is very large and the output voltage is held constant at V0. These restrictions will be relaxed later to show the effects of finite capacitance, right? So initially what we consider that this capacitor is very, very large, and because this capacitor voltage also taken as the load resistance, load voltage, that's why this for the steady state analysis purpose, this output voltage is assumed to be constant, right? And later on we introduce ripple into it, and then we see how this capacitor value affects the ripple in output voltage, right? So that is the third one. The fourth one is that is not kind of assumptions, that is the thing only, that switching period is, that is the kind of variables, that switching period is T. It means switching is operated at certain frequency with certain duty cycle T, where this 1 upon T is F, and D is duty cycle. So your on time will be D into T, off time will be 1 minus T into T. This is the basic result. And yeah, important one. In this first case, we consider that components are ideal. There is no loss. It means 100% efficiency, right? So the key to the analysis for determining the output voltage we know is to examine the inductor current and inductor voltage first for the switch closed and then for the switch open. The net change in inductor current over one period must be zero for steady state operation. The average inductor voltage is zero. So this thing is same as we have discussed here, this generalized principles. So we do apply. So when switch is on, so this is VL. As I said, we denote all the current and voltages while doing the analysis. So when switch is on, then our VLT, this VLT is nothing but VG minus VC. Yeah? So this is VC, which is same as VT. Here V output or VT is same as VT. So VLT is equal to VG minus V naught, right? Minus V naught equal to L di by dt. So from here di by dt is Vg minus V naught upon L, and because this is a buck converter, output voltage is greater than, sorry, output voltage is less than the input voltage, so this value is always greater than 0. It means this slope is greater than 0, and we have considered CCM mode. It means it will start from 0 and it will increase right up to this point, up to dt point, because this mode is on till dt. And what is the voltage here? VL is Vg minus V naught. So this is Vg minus V naught. This is the inductor voltage, right? Now after that, since the derivative of the current is positive, the current increases linearly. That is true. That's what we have drawn. So from here, if I simplify this for del I, this DIL, then this is Vg minus V naught upon L into dt, right? So if I take this value from here to here, this is the change in the inductor current during on period or when switch is closed. So this change in inductor current, which is delta IL closed, that is Vg minus V naught upon L. And what is the time taken for this del t dt? So if I multiply this by dt, then this time gives me del IL closed. Okay, so this del IL closed is this value. Similarly, we can analysis when switch is off, dt to t. So when switch is off, then this VL is equal to minus V naught, right? VL is equal to minus V naught, and this VL is LDI by dt. So from here, LDI by dt, sorry, di by dt comes out to be minus V naught upon L. So this value is negative, right? It means slope is negative. So after this period, after t equal to dt, during this period, this inductor current decreases. Inductor current decreases. Same, because the derivative of the current is negative. That's why current decreases linearly. Now, what is the value of inductor voltage during this period? Minus V naught. So this is minus V naught. This was your V input or VG, you can say. VG minus VS, VG, V input all are same, minus V naught. So the change in inductor current during this period, if I want to know, Then this slope, if I multiply with this time, then I can get this change in current. So that is del IL open, means when switch is off, switch is open, then that del IL is equal to minus V naught upon L. So from here I can write. So this del IL open is equal to minus V naught upon L, and dt, what is this period? 1 minus J into T. So this is del IL open. Okay. So as we have seen, the net change in the inductor current over one period should be zero. That is our first criteria which we should apply while doing the analysis. It means both currents should be zero. The sum of del IL open and sum of del IL close, that should be zero. So we put both the expressions over here. We get simplify, this T cancel out, right? And after that, this L will go into zero. So this is Vg minus V node into D minus V node 1 minus D equal to 0. You simplify D into Vg minus D into V node minus V node plus D into V node equal to 0. This will cancel out. From here, V node equal to D into Vg, right? So this is our expression for output voltage. It means, and we know the D value of D is between 0 to 1. That's why our output voltage will be 0 between 0 to Vg. The buck converter produces an output voltage that is less than the input voltage, right? So that is there. It means if you draw this with respect to duty cycle, then this will be kind of linearly increasing. Duty cycle 0 to 1. I cannot go beyond 1 because duty cycle cannot be greater than 1. Many times some students make this mistake. They simplify a numerical and get the value of D equal to, let's say, 2. And they say, okay, we have done well. No, duty cycle cannot be greater than 1. Why it cannot be? Because duty cycle is the ratio of T on upon T. So T on cannot be greater than T. T is the maximum limit of T on, right? So that is the reason, right? So yeah, so this is up to V in. So this is the way we can get the output voltage. Another way to find the output voltage is volt second balance, right? Volt second balance. Volt second balance. So what is the volt second balance? Basically, we find the inductor voltage during switch on. So inductor voltage is Vg minus V naught, here minus V. So Vg minus V naught for how much period? Dt plus, then next is minus V naught for how much period? 1 minus dt into 0. Now we can simplify this, and you can see this is same equation, T get cancelled. So again d Vg minus V naught minus V naught plus d into V naught equal to 0. So this will cancel out. Again it gives V naught equal to d into Vg, same expressions, right? The third way is that since the average inductor voltage is 0 for periodic operation, so what we can do, Vs minus V naught for how much period? Dt period, and minus V naught 1 minus dt. So this is also the, this is coming average voltage across inductor should be 0 over a period that is same as volt second balance. So from here we can get the output voltage, right? Now second thing is that, another thing, the capacitor, average capacitor current should be 0. So what is the capacitor current in this case? When switch is on, what is the capacitor current? So capacitor current in this case is Ig equal to IL minus I naught, right? Ig equal to IL minus I naught, and here in this case IC equal to IL minus I naught. What is I naught here? V naught upon R, right? So if the average capacitor current should be 0, it means in first case IL minus I naught, right, for dt period, plus second case IL minus I naught for 1 minus dt period, that should be 0. So if you simplify this, this cancel out. So this is IL minus I naught equal to 0. It means IL should be equal to I naught. And what was the I naught? V naught upon R. So this is this expression we get. So we got inductor current is equal to the load current, which is equal to V naught upon R. Now next is, so this was our inductor current, right? This was our inductor current. So now next is that how to find maximum inductor current or minimum inductor current. So our inductor current is rising from IL minimum to IL maximum, then IL minimum, then IL maximum in every cycle. It means this ripple del IL is nothing but difference of IL max and IL minimum. Difference of IL max and IL minimum. That is del IL. So from this, if I find this IL average, then what is this distance? This is del IL by 2 and this is also del IL by 2, right? So IL max will be capital IL plus del IL by 2 and IL minimum will be IL minimum is equal to IL minus del IL by 2, right? Now how IL we have got V naught upon R, but what is del IL? How to get the del IL? That is the another thing. So del IL we can find from any of these two expressions, either this expression or this expression. Now this expression is a bit simpler to me. So from here del IL I can get V naught upon L into dt, this one, right? So this is the del IL only. So this del IL I will put here. What is this del IL? Yeah, this one. So if I take this one, yeah. So this is V naught upon L 1 minus dt. Yeah. So V naught upon L 1 minus t into t. This value I have put. Half will be there, and this is the value of del IL. V naught upon L 1 minus d into t. Right? So I have taken V naught to be out. It is 1 upon R plus 1 minus d upon 2LF. Right? Similarly here, this is IL minus del IL by 2. So only changes in this plus minus. So one will be above the average value, one will be below the average value. Well, now we want to find the value of inductance. The value of inductance, value of critical inductance basically for the converter to operate in CCM, for the converter to operate in CCM. So for that purpose, this IL minimum, as we have already discussed, it means if this current, this converter need to operate in continuous current conduction mode, then this IL minimum should be greater than 0. It means what is the worst case or boundary condition when IL minimum becomes 0, right? When IL minimum becomes 0, that is the boundary condition. Otherwise, IL minimum should be always greater than 0. So IL minimum that should be greater than 0 for CCM operation. What is the expression of IL minimum? This expression. It means V naught upon R 1 minus 2LF. That should be greater than 0. It means 1 upon R should be greater than 1 minus D upon 2LF. It means L should be greater than R1 minus D upon 2F. Okay. So this value of inductance should be always greater than 1 minus D into R upon 2F for CCM. So for boundary condition, this L, which is known as L critical, that should be R1 minus D upon 2F for a buck converter. It means I am given the value of R, which is the load, duty cycle I have obtained, frequency I know. Based upon that, I can find the value of L critical. And L critical is just giving me boundary condition, and I want my converter should operate in CCM. So when I choose the L, that L should be sufficiently larger than L critical, and normally we take it to be 5 to 10 times of L critical. Normally we take it to be 5 to 10 times of L critical times. Okay, so that is how L is being calculated. L minimum is being calculated, which is also given here. Okay, now another way is to find this, like input power should be equal to output power. So input power is equal to V input and I input, V output equal to I output. So we can find this ratio V output upon V input equal to V input upon V output, and this ratio is D. So from here we can find I input or IS, that is equal to D into output power. How to design the capacitor for an ideal converter? Any doubts so far? Please ask. If there is any doubt, please ask. Let us take 2 minutes break to ask the doubt. Any doubt, please? No? Okay, let us go ahead. Uh, Capacitor design. So we know that our converter was like this. Okay, where this VC capacitor voltage was same as output voltage. This is the inductor voltage, and this is the inductor current IL, and this current was a capacitor current, and this is the load current, right? So our IC was inductor current minus, if I apply the KCL at this node, minus I node. So IL minus V node upon R. This is my capacitor current. So this is our IL and this is our I node. If I subtract the, I do minus this I node from IL waveform, then I get the IC waveform, and that is how I get these IC waveforms, by subtracting the I node from IL waveform, right? Now with the help of this waveform, we will find the capacitor. We have one formula, this formula, del I equal to del Q upon del T, right? So del Q is nothing but I dt, right? If I want to find the value of charge stored for certain interval, then I will just integrate the current flowing through capacitor from 0 to t. I will get the total charge stored for that particular interval, right? That is the one thing we know. Another thing, this formula we know, Q equal to C into V naught, or we can say del Q equal to C into del V naught. What is the meaning of it? Meaning of it is that a capacitor is there. If it stores certain charge del Q naught for certain time interval, then obviously net charge means it either it's a positive or it's a negative. So let's say it's a positive, then that positive charge will increase voltage to certain value, right? V naught. So what is the relation between that? Del Q equal to C into del V naught. So from here, del V naught equal to del Q upon C, that is there. Now, how to find this del Q? So I just explained here, del Q is integration of 0 to t I dt. So one way is that if I want to find, so yeah, first thing learn that I want to find del Q C del V naught. So I can find either positive charge I can take for over one cycle, either positive charge or negative charge. Let us say I'm saying the positive charge. So when this current is flowing from this point to this point, it means this is a capacitor. Original direction is like this, but current is negative. It means it is discharging. When it is discharging, it means our voltage is decreasing. Our voltage is decreasing. When this is a positive charge during this, right, it means during this period our capacitor is charging. Then again this is the negative current. So during this period again my capacitor is being discharging. So this is the entire story over one switching cycle, over one switching cycle. It means from here to here my capacitor is charging, and then rest of the period it is getting discharging. So I will take only one uh, period when either voltage charges or discharges. So let's say charges. So during this, my voltage is coming from V node minimum to V node maximum. Maximum. So change in the voltage is del V node, which is V node max minus V node minimum. And during this, del Q charge is there. So if I know from here to here this current expression, this current expression and this current expression, then I can integrate it and I can find del Q. That is the one normal way. Another way out is that if, as this equation suggests, the IDT means integration of this. So if I take this area under this curve I, then this will also give me del Q, right? So what is the area under this curve if I plot it, if I do it? So this del Q, this del Q is area under this curve. So this is nothing but a triangle shape. So triangle's area is half into base. So from this point to this point, this is T by 2 into height. So height is, this is not del IL, this is del IL by 2. Total is del IL. From here to here, this is del IL. So this height is del IL by 2. Del IL by 2. Right? So it becomes T into del IL upon 8. Right? So that is a del Q. That's what it is given here. T del IL upon 8. Now this is the del Q. So it means this should be equal to this term. So I'm writing like that only. This should be equal to C into del V naught. Right? So from here del V naught comes out to be T into IL upon 8C. So we can put the value of del IL again from here. Just del IL we have put from here this value. So let me copy this one. So this is the value of del IL. Put it here back. put it here. So that's del V node equal to T upon 8C, V node upon L, 1 minus dt. So V node, V node, 1 minus D, 1 minus D. This T square becomes F square, 1 upon F square, T equal to 1 by F. So T square in numerator becomes F square in denominator, and then 8LC, right? So this is the value of del V naught. Now we can find from here del V naught to V naught, that is equal to 1 minus D 8 LC F square. So this is the value of ripple. Initially, if you remember, we said that we are considering output voltage to be constant, but while designing the capacitor, we relax this condition, right? And we consider that there is a ripple del V node in the output, and this gives per unit output voltage ripple. This gives per unit output voltage ripple 1 minus d upon HCF square. So if capacitance value is given, inductance value we have. What is this inductance value? This inductance value is same as we have just here. We have taken this 5 to 10 times. This is the L value we need to put here. Then we can find this per unit output voltage ripple, or if per unit output voltage ripple or percentage output voltage ripple is given to us, and then we can design a capacitor. That is also possible. We can design a capacitor when per unit output voltage ripple is given to us. So C is equal to 1 minus D upon 8L del V naught upon V naught into F square. That is the value of capacitance, right? When everything is given. So what we can see from here, that if F is increased, then you can see that C value is decreased. CFC is proportional to 1 upon F square. So that is the reason that we want the devices which can operate at higher frequency, because if such devices are there, then which can operate at high frequency, which can allow us to operate high frequency, then this value of capacitance becomes very less, and this further reduces the size of our system. And similarly, for this inductance, if here we see that this L is also proportional to 1 by F. So if F is increased, then this value of inductance also decreases. So here also we see that the impact of increasing the switching frequency, the size of inductance also reduces. So this is always advantageous for us if we can operate the system to be at higher frequency. This will help us to reduce the size, right? So we will see further that del V node upon V node, if this value is lesser, then value of C should be higher. It means if we want less output voltage ripple, that means we need to go near to DC voltage, then value of capacitance should be very, very high. But as value of capacitance becomes very, very high, then its cost increases, its size increases. So we allow certain percentage of ripple. Ideally, 1% to 2% ripple we do allow in output voltage, right? Until unless this is very, very high precision application is there, right? So we allow 1% to 2% output voltage ripple. Well, so any doubts so far before we go to next topic? Okay, so we take here 5 minutes break again, and we'll be coming back after 5 minutes. You can take 5 minutes. So 1 hour lecture is left. Few more topics on this. We'll be back after 5 minutes. Meanwhile, if you have any queries, please type it in chat box. And how to know? Well, okay, so let us proceed. Okay, so this is we have done. We have discussed that how to design. We have taken the example of a buck converter and discussed how to design its parameters, L and C specifically, right? So this frequency is, the parameter which is in hand of a designer. Now, the designer may choose this frequency and accordingly L and C will be varied, right? Now, let us see the impact of this known idealities on the design parameters. Okay, well, so this is very interesting. We will see the some findings which is very interesting when we include the known idealities. So this is the ideal circuit which we have used here. Okay, and this is the known ideal circuit. So what is the difference? So here we had one switch. We had this one switch over here. Here also we are having switch, right? But as we know that when switch is on, then there is some losses. And in order to represent those losses, we have considered one resistance which is denoted as RSW in the switch, right? So this entire part denotes a switch, right? Just for analysis purpose, we have taken this RSW inside, but this is a command package, right, within the switch itself. Similarly, we have inductor. So as I said, ideally inductor is lossless, but practically this inductor has some resistance. And when current flows through this inductor, due to that resistance, there is a power loss. So in order to represent that power loss, we have taken one resistance RL in series with this inductance, and this is called ESR. ESR, equivalent series resistance of the inductance. This is called ESR. Equivalent series resistance. Okay. Similarly, this capacitor, ideally this is lossless, but practically it also has losses. So to represent that losses, we put a small resistance which is called ESR of the capacitor in series with this. When diode is there, ideally diode has zero losses, but when practically this is on, then it has the forward voltage drop as well as it has certain more losses. So RD is the diode forward resistance and VF is the diode forward voltage drop. So what we have done here, we have represented every component of the converter along with its associated power loss, right? RSW, RL, VF, RD, RC. So after inclusion of these known, and these are called parasitics, or you can say non-idealities. After inclusion of these non-idealities, the behavior or the performance of the converter becomes entirely different. Let us see how does. So everything is given in this paper. Springer paper is there. In this analysis is given. If you need more detail, you can read this paper. Okay. So how to do the analysis in the same way which we have done for the ideal converter. So DC to DC converter, buck converter, when switch is on, so switch was on, it means this is on and diode was here. So diode is off, right? First mode 0 say DT. Then DT to T another mode in which this switch which was here that is off right? And this diode is on, right? We'll see it. Now switch is on, then switch is represented by its resistance RSW, right? And this is off. It means this diode is entirely off. Inductor is represented by RL, like that. This is the equivalent circuit. Now the procedure remains same. We write the equation for this VL on, right? So this is VL on means when switch is on, so VL on. So VL on equal to L di by dt, which is equal to, so we can write, we can start from here like that, Vg minus, this is ISW and IL is same, so RSW into IL minus VL minus RLIL, right, minus V naught equal to 0. This is the equation. So from here VL is equal to L di by dt is equal to Vg, this Vg minus this term and this term are together, RSW plus RL into IL minus V naught. Like that we simplified. And second, capacitor current we write. So capacitor current IC on T is equal to IL minus this current IL minus I naught, which is V naught upon R. This equation. And what is the V output in on condition? VC. So here you see earlier this capacitor voltage was same as output voltage, but now not the case because RC is there. So V naught will be equal to VC, this VC plus RC into IC. VC plus IC into RC. So these three equations we have obtained. Now switch is off. Because switch is off, now inductor current was increasing, suddenly you have made the switch to be off. Now this inductor current has no way to increase further, so it will try to decrease. When it try to decrease, then this LDI by dt becomes negative. This inductor changes the polarity, which in turn force this diode to be on. This diode becomes on, and this is the equivalent circuit in this case. In this case, when we write the equation, so you can start from anywhere. Let's from here. So 0 minus VL minus ILRL minus V naught minus VF minus, and because this current ID is same as IL in this case, so minus RD into IL equal to 0. Okay, so you can simplify this for VL. This is VL. Let us check. This is VL. Okay. So this term is that side. Then minus IRL. So this is minus IRL. Minus V node. Minus V node. Minus VF. Minus VF. Minus RDRL. Minus RDRL. So like that we have written this equation for. Again we apply the KCL over here. So this IL is equal to IC minus I node. IL equal to IC minus I node. That is V node upon R. Second equation is written, then VC off. So this VC off is same as VC plus IC into RC, VC plus IC into RC. So three equation this side, three equation this side. We have written 6 equations. So these equations has been written. Now we will again do the steady state analysis. So as discussed earlier, we use few principles. That is the first inductor volt second balance. We do DIL. This is the inductor voltage balance. So using this equation, we put D. So let me write here only. So this equation is D into Vg minus RSW plus RL into IL minus V naught plus 1 minus D minus RD plus RL into IL minus VF minus V naught, that should be equal to 0. This is your equation, right? So if we simplify this equation from here, you can get D into Vg, right? Then this is D into V naught and 1 minus D into V naught. So this becomes V naught and minus sign when it goes to right side it becomes plus. So this term is covered, this term is covered, this term is covered. Now another term is that 1 minus d into bf. It goes to right hand side, then it becomes d dash bf. So this term is covered. Now what is left? Only left is d into rs, d into rl plus 1 minus d into rl. So when this term goes to right hand side, this becomes rl. Now what is left? D into rsw. So d into rsw, then 1 minus d into rd, 1 minus d into rd. Where what is the d dash here? D dash is nothing but 1 minus d. Okay, so this equation is obtained. Now the second thing which we do apply is the capacitor charge balance. So in capacitor charge balance, d into IC on plus 1 minus d into IC off, right? So d into this plus 1 minus d into this, both are the same equation. So d plus 1 minus d equal to 1. So from here IL becomes V node upon R equal to I node. Okay. Similarly, we can do the average output voltage dV on T plus 1 minus dV of T. So both equations are same, right? So this becomes Vc plus Ic into capital R Ic, capital Ic 0, average current is 0, so V output equal to Vc. So from here, what we get, just let me redo everything. So well, so these three major equations we have got. One is this one. So yeah. So we got one equation this, another equation this one, and the third equation this one from here, right? Still we have not obtained the output voltage. Our aim was to obtain the output voltage expressions, right? So what we do here, IL is coming into picture. So we will put IL equal to V naught upon R into this expression. Okay. We will put IL equal to V naught upon R into this expression. So that is putting 10 into 8. Putting 10 into 8. So let us put this. So this is dVg equal to d dash Vf plus V naught RL plus dRsW plus d dash Rd into IL will be replaced by V naught upon R equal to 0. That is equal to dVg equal to d dash Vf plus V naught. This is plus, yeah, plus V naught plus. So I'll take this to be common. V naught to be, this becomes 1 plus 1 upon R. RL plus dRsW plus d dash Rd. Well, so it becomes from here V naught equal to, so one more thing we can do, d into Vg equal to V naught also will take totally common 1 plus d dash Vf upon V naught plus 1 upon R RL plus dRsW plus d dash Rd. And from here now we can find V naught, which gives me this expression, right? V naught equal to dVg upon 1 plus d dash Vf upon V naught plus RL plus dRsW plus d dash Rd upon R. So this is our output voltage expression if we are considering the known idealities into picture. But in ideal case, our expression was V naught equal to dVg, right? But in non-ideal case, this is the expression. So what we conclude from here, that as you can see, this term is 1 plus something. First you just consider, if I put everything non-ideal to be 0, RL to be 0, RSW to be 0, RA to be 0. This term is 0, and then VF to be 0. This term is 0, and that term is 0. So I'm getting this expression. Fine. Now, as this term is greater than 1, it means this V output is less than D into VG, right? So this entire term V naught non-ideal, which is this one non-ideal, that is always less than D into VG, right? So what does that mean? That in non-ideal case, the output voltage is less than the desired voltage, which is D into VG. Why it is happening? Why this voltage is less? This is happening because there are voltage drop. You have set certain duty cycle. For example, I take one numerical example. Let's say you had set input voltage to be 20 volt. You wanted output voltage to be 10 volt. Ideally, duty cycle was 0.5. You have set duty cycle to be 0.5. Input voltage is 20. You expected output voltage to be 10 volt. Ideally, if it is there, it will follow this equation well. But practically, what will happen? You have given 20 volt, duty cycle is 0.5. In between, there are non-ideal elements. Resistances are there in every element when they are switch on, when they are switch off, right? So due to that resistance, there will be certain voltage drop. Now there will be voltage drop. So due to this voltage drop, the final output, which is reaching to the resistance to the load, that will get reduced, right? That will get reduced, and which is given by this expression. Now what is the remedy? How can I get? So one way is that if I increase the input voltage, then I may get 10 volt. If I say instead of 20 volt I do it 22, then I can get, or if I rearrange the terms and I simplify this for duty cycle, then I will get this particular expression. And in this expression, if I put the all values of non-idealities and the desired output voltage, then I will get the actual duty cycle which is required. Or this duty cycle, if it is put, or at this duty cycle, if switches are operated, then I will get 10 volt only, right? So this duty cycle expression tells me that this value of D is greater than D ideal, and that must be there, that should be there. So if D is greater than D ideal, then your output voltage will be what you desire, what you have set, what you want, right? It means duty cycle should be increased in order to compensate the voltage drop appearing across the different non-ideal elements. So I give simple example. Let's say I have asked some student, I have given 100 rupees to him, and I have asked to perform certain task, go to market, and then bring those things worth 100 rupees, right? Let's say I say bring 2 kg sugar. Let's assume 1,500 rupees per kg. I have given 100 rupees. Now market is 2 kilometers away. What I am thinking that the student is going to market, just bringing 2 kg sugar to me. But I have not added anything in between. Okay, he will go by auto or something. Let's say he goes by auto. Ideally, I'm thinking that he will just go and will take it. No, but if let's say he goes by auto and he spends some 20 rupees on auto while bringing this. So ultimately, he will be having 80 rupees in his hand only, right? And he will bring some sugar worth 80 rupees to me. I will say sugar is less. It is not 2 kg. It is 1.6 only. Then obviously it has to be 1.6 because he has to spend, practical case is that he has to spend 20 rupees for the auto. right? So if I want 2 kg sugar, then what I should do? I should give him some more money, 120 rupees. So 20 he spends, then 400 rupees, he will do the useful work and will bring. Then my job is done, right? So the same thing is here. Now, because non-idealities are with me, so that voltage drop I need to take into account. And for that, I have to keep the switches on for more time. Increasing duty cycle means to keep the switch on for more time so that more current can flow, the current can flow more time, voltage may be applied for more time, and the output across the load can be achieved what we want, right? So this expression is plotted for output voltage with respect to duty cycle for both the cases, ideal case and non-ideal case. So ideal case line is the blue one and non-ideal case is the green one. You will see that ideal case line is always falling below the non-ideal case. What does that mean? That if I fix certain duty cycle, or you can say I fix certain voltage, let's say 10 volt, keeping the input voltage to be same, then in order to get the 10 volt from the non-ideal converter, I have to have more duty cycle. I have to have more duty cycle, right? So duty cycle I need to increase for that purpose. And moreover, in ideal case, this duty cycle, output voltage expression was not function of load resistance, right? But here this function is this expression is function of load resistance as well. So we have plotted these characteristics over here. This first one, the left one, gives the output voltage variation with duty cycle at various load resistances and constant Vg. So we have kept the input voltage to be constant and the load resistance is varying here. So we compare this blue one, this blue one is the characteristics for ideal one, ideal case, right? And then there are green, there are three more characteristics here. For this is first one, near to ideal is for R3, then R2, then R1. These characteristics are there, a different value of R, right? Such that R3 is greater than R2 is greater than R1. It means what is happening here when I am reducing the R1. Reducing R1 means increasing the load. It means when I am increasing the load on the converter, then for the same duty cycle, if I keep the duty cycle to be same, you can say, let's say this duty cycle I always keep 0.6 for example, right? So what is happening here, as I'm increasing the load, then output voltage is decreasing. Ideally, this should be there, but I increase the load, then drop, then further increase, drop, then further increase, drop. Resistance is decreasing, load means load is increasing, right? So if I'm increasing the load, then my output voltage is decreasing. So in this case, output voltage becomes dependent on the load itself. Load itself, right? More the load, more the drop. More the drop, lesser the output voltage. First conclusion. Second, output voltage variation with duty cycle at various Vg and constant R. Now I kept R to be constant and then increase the V, right? So when I see here, then I can compare these results. You can see there are few results. So let us compare these results as a combination of two. So this is when I keep some Vg, then I compared with ideal and non-ideal. So such that this Vg3 is more, Vg2 is lesser, Vg1 is further lesser, right? And what we seen here, that in all these cases, right, in ideal case, if you keep the any duty cycle, let's say this duty cycle, then our voltage in ideal case is always more, right? Voltage in ideal case is always more, and in non-ideal case it is always less. And as you are decreasing the voltage, then this gap is also decreasing. The difference between these voltages of non-ideal and ideal case are also decreasing, right? And these characteristics were plotted based upon this formula for non-ideal case, and for ideal case it was d into vg, right? In one case, first case, we have kept input voltage to be constant. In another case, we have kept the load resistance to be constant, varying the input voltage. Right, so this is how impact of this non-idealities is there on the output voltage. Any questions, please? Just take 2 minutes if you have any question. Let me ask if there is any query. Well, so okay, let us proceed if there is no query. Uh, so in ideal case, we have found the value of inductor current, right? Similarly, we can calculate the value of inductor current we have found the value of inductance, right? Similarly, we can find the value of inductance in this case also. So if you remember the L value which was there, it was found based upon this formula IL minimum, which is equal to IL average minus del IL by 2, right? And then we have put this value of del IL to be V naught 1 minus D upon LF, like that it was found. Similarly, we can found it here as well. And let us say that XL is defined as the inductor current ripple factor, where XL is equal to del IL equal to XL into IL, right? So XL is defined here del IL upon IL. So in this case, we found it like considering IL minimum to be 0. So for this del IL was 2 into IL. So if we say XL value is 2, it means 200% ripple, right? So you can consider it in this way. This is your IL, right? And this is your del IL. So below this there is del IL by 2. Below this there is del IL by 2. So from here, ripple is 2IL. Below this 100%, below this 100%. It means 200% ripple is there. That is the critical case. So that's why we take it to be 5 to 10 times. But if we are given with exact ripple, that 10%, 20%, maximum 200%, if this is the value of ripple current which can be there, then accordingly we find XL, right? And value of L. So based upon that we find this. So del IL equal to XIL. Now what is the del IL, right? So in this case we can find del IL from these equations from here. So from here what can be del IL? Like del IL from here will be, because we need magnitude, that's why this is RD plus RL IL plus BF plus V naught upon L. This is the value of del IL. So let us use this value over there. So this is the value of del IL. Now from here you just put del IL equal to X into IL and simplify del IL equal to X L into IL and simplify this equation for L. Then what you will find? What you will find? 1 minus dr upon xlf, 1 plus vf upon r, rd plus rl, like this you'll find. So this is the value of inductance, right? If you simplify this and put the value of IL also, then you will find this expression. But in okay, so in this case this is for non-ideal. For ideal case, what you will do, you will put all values to be 0, rd 0, this 0, this 0, then this entire terms, then this entire terms collapse. It is 1 only. So 1 minus dr upon xl into f, which is the same as we had already with us. The r1 minus d upon 2f, xl equal to 2. So if we plot both the equations for inductance value with respect to duty cycle d, then these are the expressions. Now, if duty cycle is kept same, let's say 0.4, then this is the value of inductance, and if non-ideal case, this is the value of inductance. So what we are getting from here, that in non-ideal case, the required value of inductance is more. The required value of inductance is more than the ideal case. So if I need to properly design the inductance for a non-ideal case, then I must use this particular formula. And this formula gives me the exact value of inductance, right? Well, now next step is how to design the capacitance for a non-ideal buck converter. This is very important topic. So we will discuss few steps that how to design the capacitance in this case, right? So let us see here. Earlier, this output voltage was same as this voltage VC, right? So output voltage and DC both were same. So there was no issue. We could find the del VC here, and then that could be del V node equal to del V node. But in this case, this ripple is there and RC is also there. So the del V node ripple will be equal to the combined ripple of this VC and RC, right? So in order to find the capacitance for that, so you can see in these waveforms here also, this waveforms here. This is the capacitor current. This is the capacitor current, right? Now, current IC is flowing in this. Now this IC into RC will be having certain voltage drop. So IC into RC is having certain voltage drop, means this one. This will follow the same current shape. So this is IC into RC, right? Plus VC. So this is your VC, right? So sum of these two will be ripple across output voltage. Sum of these two will be the ripple across this output voltage. That is there, right? So how to find this? So in order to find this, there are certain ways, right? So we can write the equation for this capacitor current. We can write the equation for this capacitor current. Okay, so I just give some hints. So let's say during we do analysis during switch on case. So when switch is on, then we can write the equation for this period. So ICT in this period will be del ILT upon TT minus del IL by 2. So if you put T equal to 0 in this, then you can see this is minus del IL by 2. If you put T equal to dt by 2, this dt by 2, then you will see that value is 0. Likewise, you can see up to here, right? If you put T equal to this entire value dt by 2 plus 1, T by 2 if you put, then you will get this value, right? So this is the IC we get. Now, once if we get IC, then what is the VRC? RC into IC, that we can find, right? So this value just RC into ILT, not ILT, del IL upon dt into T minus del IL upon T. Okay, so this we can get. And now what is the del VC? Del VC is nothing but 1 upon C, 0 to T ICT dt plus initial voltage, right? So likewise, we have written these two equations, and you put the value of IC here, right? After substituting this value of IC, you integrate, then you will get certain equation. I'm just writing directly. I'm skipping one step here. T upon dt minus 1 plus del Vc 0. Right? So addition of these two will give us del V naught, which is del VRC plus del Vc. So that is the very first equations we get. Similarly, when switch is off, the more analysis you can follow in my paper, that is over there. Similarly, when switch is off, then we write same equations, and after writing same equations, we For a given del V node, for a given del V node upon V node, we find the value of C minimum, and this C minimum expression is given as shown here, right? And what we see here that this C minimum depends upon RC, right? On value of RC. More the RC, then more is the value of C minimum. RC is here also. So more the RC, then more is the value of C minimum. It means if effect of ESR is more, then more capacitance is required, right? So let us take these values of these parameters. Okay. Any doubts so far? No. Huh? Okay. We will see the impact of these parameters now, these ESRs now. So parameters used for simulation. Let's say input voltage is 20 volt. Input voltage is 20 volt V input. Then V output we need 12 volt. So ideally, what is the duty cycle? If we use the formula that V output upon Vg, then this should be 0.6, right? And load resistance is 10 ohm, frequency is 20 kilohertz. Now inductance is 490 microhenry, but its ESR is 0.5 volt, right? Capacitance is 50 microfarad. Diode forward voltage is 0.5. Switch when it is on, then resistance is 0.05 ohm. And for diode, when this is on, then diode resistance is 0.03 ohm. Inductor current ripple is XL equal to del IL upon IL, right? And output voltage ripple, we need 1% or this 0.01 per unit. This is our desired specifications given. 40% current ripple, 1% output voltage, and these are the ESR. Now we need to design a converter, right? So as I said, ideally if I follow, then duty cycle is 0.6, right? But if I apply 0.6 duty cycle with a 20 volt input, and if converter is taken ideal, output voltage will be 12 volt. But if it is not the case, then converter output voltage will be something different. We will see it. So in order to improve that, what we need to do? We need to increase the duty cycle. So how to get the particular duty cycle? This one, using no. Is it possible to cut this? Okay, so actually this is not being copied. So just in this formula, if you put all the known identities, you will get the value of D. So here, in that case, duty cycle comes out to be 0.6415. Duty cycle comes out to be 0.6415. Similarly, if you use the value of these known idealities in L, then using the ideal formula, it is 448 microhenry. But using the formulas which were derived using the non-ideal elements, this comes out to be 490 microhenry. So what we have seen that there is increased inductance. It means more inductance is required. And the value of ESR, which is maximum allowed. Okay, I have not explained what is the maximum allowed ESR. Yeah, yes. So if you see here this capacitance formula, right? Then you will see that this term should be, in order to have particular C minimum exist, this term which is under square root, that should be real term. That should be real term, and this value should be greater than 0. Value which is under the square root, that should be greater than 0. If this value is greater than 0, that puts the restrictions on RC, right? So that value is called the RC max. So if your capacitance is not available with that RC max, then it means you cannot achieve the desired ripple voltage. That is the meaning of RC max. So if I calculate the value of RC max, that is 0.2398 ohm for 1% output voltage ripple. So the capacitor which we are using here is should have the ESR less than this, and our capacitor was having zero point 0.1 ohm ESR only, right? Ideally, if we calculate the value of capacitance is 25 microfarad, but using the improved formula, it is 50 microfarad. So how does this results improves? Let us see. Output voltage response for ideal and non-ideal duty cycle. As I said earlier, if I am keeping duty cycle to be 0.6, I expect that output voltage should be 12 volt, but it is not coming 12 volt. It is less than 12 volt. It is less than it is less than 12 volt. It is 11.2 somewhere, right? But with the same converter, I'm not changing the converter. I'm keeping the converter to be same, right? With the same converter, if I'm increasing duty cycle from 0.6 to 0.615, 0.6415, what is this point? How this value have been received? 0.6415 by putting the non-ideal elements value, right? So if I'm increasing this duty cycle to this value, then my converter output is reaching to 12 volt. It means, what does it mean? It means if I can increase the duty cycle with the improved formula, then I will get the output voltage same as the desired one. And we can see here the same, the first one is the simulation result. So I will try to show you in tomorrow's class that how we can do the simulations. And this right one is the experimental result. So in experimental result also, I kept 0.6 duty cycle, output voltage was 11.2, and then we increased the duty cycle to 0.4, 0.642. The output voltage was 12 volt, right? So that means it is verified in experiments also. In experiment, whatever converter we have, that is a real converter, practical converter only, and from there we have taken these values of parasitics and added them, right? So we can see impact over here. Now, any doubt, please let me ask. You can ask any doubt if you have. Okay, no doubt. So we shall proceed further. So this is yeah. Now this is the what is the impact of ESR on the output voltage we will see. So we have seen that our RC max is what is the value? 0.24. 0.24 ohm, right? It means if and capacitance value we have taken to be 50 microfarad, and for ideal case it was 25 microfarad, right? So if I do not have any RC, it means RC is 0. That is the ideal case. In simulation, I can have RC equal to 0, but in experiments, I cannot have, right? In experiments, I cannot have RC to be uh, 0, because capacitor is the physical entity, and that physical entity will have certain resistance in it, right? Hmm? Now, In simulation, I kept RC equal to 0. It means it is having no ideality. So if for that case, my capacitance calculate is 25 microfarad for 1% output voltage ripple. So 1% output voltage ripple means my output is 12 volt. So del V naught is 1% of this 12 volt. So that is 0.12 volt, that is 120 millivolt. It means if I am using a capacitance of 25 microfarad, maximum I can have 120 millivolt ripple. But because my capacitance is 50 microfarad, so definitely my ripple will also reduce. So my ripple is now, you can see here, that is 0.06 volt, 0.06 volt, RC equal to 0. Now slowly what I am doing, I am increasing the ESR value, right? So and keeping the capacitance to be 50 microfarad only. So I have increased capacitance to be 0.1 ohm. Why I kept 0.1 ohm only? Because in hardware, our capacitance was also having zero point 0.1 ohm ESR. So that we kept. So because now I have increased the RC, it means my ripple will also increase. So my ripple increased from 0.6 volt to 0.07 volt, right? And because in is this first case 1, RC equal to 0, RC is 0, that's why del VRC, which is IC into RC, that will also be 0. And now del V node will be del VC plus del VRC. So same del VC, it means in this VRC will not be present and del V node and del VC will be overlapping only, right? But here RC presents. So if RC presents, then del V node, del VRC and del VC, all three will be present, and you can see all three waveforms are present here, right? This del VRC is present, red one, green one is del VC, and some of these two are your del V node. All three are present here. But still my output voltage V del V node is within the limit, which we said to be 120 millivolt, which we said to be 120 millivolt. That is within the limit. Well, now I further increased ESR to my maximum RC max, that is 0.24. So this is the limit, 0.24 for 1% OVR. Now in this case, what is output voltage ripple I'm getting? Here to here, 0.12 volt, that is 120 millivolt. And this was my limit. So it is matching. If I'm going in hardware, it was not possible because I cannot find a capacitor which is having exactly 0.24 ohm resistance. But in simulation, I can see the results, right? And this way I can find that 120 millivolt is reaching, and all three components I can observe. Then what I did, I further increased the value of RC to 0.4 ohm, right? It means my RC has crossed RC max, and as I said, there is a limit. Yes, please. कौन है? So there is a limit on RC max. So RC max, if I'm keeping to be 0.4 ohm, then what is happening? Now ripple is becoming 0.19, that is 190 millivolt. And obviously this is greater than 120 millivolt, which was my design criteria. So due to increase in RC, now my voltage ripple has increased beyond the design. It means this is not permissible. And why this is not permissible? Because I am having a capacitor which is crossing my limit, ESR limit. That's why output voltage ripple is increasing. So fourth one is not meeting my design criteria. Okay, so let us verify these things in uh, experimental work. So in experimental work, which cases are possible? Case 1, not possible because I cannot have capacitor with 0 ESR. Case 2 is possible, 0.1. Case 3, May possible, may not possible. In my case, it was not possible because I could not find any resistance having 0.24. But the fourth one, next capacitance was with me, which was having 0.4 ohm resistance, so that I have taken. So I have seen these, I have observed these voltages. So first case was not possible. R's equal to 0.1 was possible. R's equal to 0.4 was possible. So one is less than RC max, another is greater than RC max, right? So we could find that if you see here, switch is on, switch is off. So between these two limits, the output voltage ripple is 0.075 volt. So that is 75 millivolt. And in this case, the output voltage ripple is 190 millivolt, which is crossing our 120 millivolt limit. But this is less than 120 millivolt limit. It means RC equal to 0.1 ohm is giving me or is meeting my specifications. But RC equal to 0.4 ohm is not meeting my design specifications, right? So in nutshell, what I can see, what we could observe, these ESR, ESR makes an impact. ESR makes an impact on the performance, of these DC to DC converters, right? So proper impact analysis of these ESRs are very, very important, right? If we do not do it, then our performance may deteriorate, and if performance deteriorates, then we cannot find so we cannot without this non-ideal analysis, we cannot get an idea that what is the reason for this, right? So it is better in modeling also we will see these impacts of these non-idealities affects the controller design a lot, right? So as accurate as possible model we design, our controller will give good performance. So if we consider these non-ideal elements in design also, right, then certain aspects will be covered here, then certain aspects will be covered during control, means controller will do rest of the job. But if we loosely design the storage components, which is L and C, for a converter, then again controller have to put more efforts to regulate the DC voltage, right? So this how this study and impacts a lot. And moreover, like in next class, we will see that in buck converter it is impacting just that voltage is less, but in case of boost converter, this entire performance is changed. Entire theory, what we expect in ideal case, gets changed in case of boost converter. That we will see in our next class, whenever it is, maybe tomorrow or after tomorrow. So with this, I close here, and now you have 5 minutes for question answers. If any question answers, please put in chat box. I will try to answer. And for the schedule of tomorrow's, I will put in WhatsApp group. Thank you. If there is any question, you may ask, please. ESR means, yes, ESR means equivalent series resistance. So basically, madam, I have explained this in this slide. Let me explain again. Yes. So in this slide, we explained this, that one is the ideal converter, another is a non-ideal converter. So in ideal converter, we consider that the losses in each component is 0. ideally, right? But in practical converter, that is not possible, because you're like, inductor. Inductor is made up of copper wire, right? On a ferrite core or some core is there. On that core, this wire is there. So this wire is made up of copper. Now, this copper has some resistance, right? So whenever there is a current through this, obviously it will show the inductance property, but along with that, this current will have losses. So in order to represent that loss, we in modeling, we define one term RL, which is the resistance of this inductance, and call it to be equivalent series resistance, ESR. This equivalent series resistance. Similarly, we do use it in capacitance also. So I hope it answers your question. Okay, fine. Thank you, thank you, thank you. And more things will be covered in coming lecture. Uh, Maybe like few things were new to you to find here. Those who really works in converter part, but those who works on power system side and like for EVs and all optimization side, they may not be aware of these things. But those who works in converter, it is very useful for them. So, if any question, please put in chat more questions. I will be happy to answer. Yes, very informative. Okay, so I just share. I think you have my number. I'm posting it, on. So you message me. I'll share over there, or you email me. I will share on email. Simulation in MATLAB version. Yeah, that we will do in our this course. We will do this MATLAB simulation also. Yes. Paper also I'll share. You write me email or just WhatsApp me. I'll share it. Thank you. Any other query, please? Maybe you write me an email. I will reply to that, please. Right now, I will not be in a position to email, but if I get your email or WhatsApp, I will send it. Thank you. Any other query, please? So tomorrow we will be having two more sessions. Yes. Then we will continue whenever my turns come. Then we will continue this topic. We have further discussions on like boost converter, then buck boost converter, then modeling of these things, then their MATLAB versions. So those things we will be discussing. Okay, so if there is no further query, anyway, you can write me an email later on if you have any query. We can stop today's session over here. So thank you very much. Now tomorrow I'll share you the schedule for tomorrow, and we'll meet tomorrow at 2 p.m. Thank you. Thank you. Okay.
Thank you, Dr. Manmohan, for insightful lecture. So guys, we will meet tomorrow same time for new sessions. Thank you.
Okay. Thank you, Anupam. Thank you all. Thank you. Have a nice day.